In the vast expanse of nothingness, before stars shone and planets spun, there was a profound silence. This was a silence not of empty space as we know it, but of no space at all. We begin our journey at the very dawn of everything, a moment when time and space themselves were just about to be born. Take a slow, deep breath and imagine the universe in its infancy, an unfathomably small, hot point containing all that would become reality. In this gentle exploration, we will traverse from that initial spark outward, through the earliest ages of the cosmos. Our pace is unhurried and calm, letting each epoch of cosmic history unfold softly before us. With a quiet mind, we drift back 13.8 billion years to witness the universe's emergence, the cosmic origins of everything we know. In the beginning, the universe was concentrated into an inconceivably dense, hot state, all of space compressed into a single point. The term Big Bang often brings to mind a fiery explosion, but it was not an explosion in space. It was an expansion of space itself. In that initial instant, about 13.8 billion years ago, the fabric of space and time began to unfurl. A searing flash of energy filled the newborn cosmos, setting everything into motion. Temperatures were so extreme that even atoms could not exist yet. Matter and energy were a blur of pure light and fundamental particles. All that we see around us today, every galaxy, star, and planet, was once cradled in that tiny, primordial point. Then, in a fraction of a second, the universe began to expand rapidly outward in all directions. As we move to the right, we see the formation of stars and galaxies, and the continuous expansion of space. Our current universe is on the far right, still expanding outward. This initial expansion was extraordinary, unimaginably swift and powerful. In fact, for a brief moment, the infant universe expanded faster than the speed of light. This doesn't violate any laws, as it was space itself stretching. Scientists call this fleeting epoch cosmic inflation, an early growth spurt of the cosmos. During inflation, the universe swelled from subatomic size to astronomical scale in a heartbeat. Scientists are not yet certain what triggered this rapid inflation. It remains one of the subtle mysteries of cosmic origins, a point of intrigue we ponder quietly. But the effects of inflation were profound. It set the stage for everything to come, imparting tiny irregularities, slight wrinkles in the very fabric of space, that would later grow into galaxies and clusters of galaxies. In the tranquility of this narration, we consider how even in such a young, fast-changing universe, these minute fluctuations were already present. They were like seeds, scattered in the hot, expanding cosmos. Seeds that would, over billions of years, give rise to stars, galaxies, and the grand cosmic web. As inflation drew to a close, the surge slowed, and the universe's expansion became more gradual. The energy driving inflation transformed into the ingredients of a newborn universe. A burst of light and a flood of elementary particles. The Big Bang, in this context, can be thought of as that moment when the universe was filled with brilliant light and matter for the first time. In the aftermath of inflation, the universe was still incredibly hot and dense, but now it was expanding at a calmer rate. We have stepped into the next chapter of cosmic history, where the bright afterglow of the Big Bang begins to fill space, and the building blocks of everything, tiny particles, dance in the heat. Now the universe is one primordial soup of energy and particles. We are about 1 second after the Big Bang. In this infant epoch, imagine an immense ocean of light and subatomic particles, all tangled together. It is blindingly bright, yet if we were somehow present, we wouldn't see in the conventional sense. The glow is everywhere and everything. Protons and neutrons, the components of atomic nuclei, are forging into existence as the universe cools slightly from its earlier fury. The temperature is still tens of billions of degrees, far hotter than the core of any star today. In this seething plasma, particles collide incessantly. It's almost like a cosmic stew, with ingredients mixing rapidly. As the seconds and minutes tick by, softly on a cosmic clock, the universe continues to expand and cool. This cooling is gentle in our narrative, though in reality it was still extremely fast and energetic. By about 3 minutes after the Big Bang, the temperature has fallen enough that some of those protons and neutrons begin to stick together. They fuse through nuclear reactions, forming the first atomic nuclei. This era is known as Big Bang nucleosynthesis. In these calm early minutes, helium is created from hydrogen. Just as water condenses out of steam when it cools, helium nuclei condense out of the hot plasma of protons and neutrons. Trace amounts of lithium and beryllium also appear. The entire universe at this point would still fit within a sphere only light minutes across, yet it contains the raw material that future stars will use as fuel. We linger on this scene, a bright, opaque universe filled with a fog of charged particles. The term soup truly fits. Electrons, protons, photons, particles of light, all move together in a dense, hot broth. Any light produced is immediately scattered by free electrons, so nothing can travel far before bumping into something else. Space is brilliantly lit, but also opaque and clouded, like a sunlit fog. If you could be there, you would feel the glow on every side, but you could not see through the haze. The young cosmos is bright and uniform, without form or structure yet. A vast, hot cloud, where darkness has never even had a chance to exist. Through this period, the universe's expansion acts like a natural cooling mechanism. As space stretches, the energy of the particles spreads out. What was once an overwhelming blaze gradually softens in intensity. Minutes turn into hours, hours to years, years to millennia. We compress this passage of time in our gentle telling. Slowly, steadily, the temperature drops from millions of degrees to hundreds of thousands of degrees, and still the cosmic fog persists. The free electrons, tiny and invisible, continue to scatter every ray of light. It will take a long while yet, hundreds of thousands of years, before the universe becomes transparent. So for now, we float in this warm, glowing cloud, awaiting the next transformation. Gradually, after about 380,000 years, the universe reaches a critical moment of change. What was once blinding plasma now cools to roughly a few thousand degrees, cool enough for electrons to gently settle down into orbits around nuclei. In this calming cosmic sea, protons, the centers of hydrogen atoms, capture electrons and become whole, neutral hydrogen atoms. Helium nuclei gather electrons to form helium atoms. This phase is poetically called recombination, though it's actually the first time these electrons and nuclei have combined. Imagine countless electrons finding their homes, like butterflies coming to rest. With this simple but profound change, the universe undergoes a beautiful transition. It becomes transparent. All the light that was once trapped in the fog is now free to travel. The cosmos, which was opaque for so long, suddenly clears up like a mist evaporating under the morning sun. Photons, particles of light, can stream across space unhindered because most of the electrons are now bound into atoms and no longer block the way. This first light to freely shine is not like the light from a star, but a gentle glow filling all of space. It is as if the universe itself is glowing softly, a warm afterglow left from its hot youth. We call this the cosmic microwave background, CMB, the very faint primordial light that still surrounds us even now. In our minds, we might picture a pale amber light suffusing the young universe, gradually dimming as space expands further, but never fully going out. This light carries with it a memory of the universe at that infant stage. Even as we relax into this narrative, that ancient light is quietly rushing past us and through us, continuously. Billions of years later, in the modern era, scientists would detect this gentle glow with radio telescopes, discovering it as a nearly uniform microwave signal coming from every direction in the sky. It's often described as the afterglow of creation, a fingerprint of the Big Bang itself. If we tune a sensitive antenna to empty space, we can still hear a faint whisper of this event in the form of low-level noise. For the purposes of our calm journey, we simply acknowledge that this light is there, a backdrop to all later cosmic history. Figure an all-sky map of the cosmic microwave background, the oldest light in the universe. This image, created from spacecraft data, shows tiny temperature fluctuations as color differences, red and yellow for slightly warmer spots, blue for slightly cooler. These subtle variations, only tens of millionths of a degree, are the seeds that eventually grew into galaxies and clusters of galaxies in later eras. In this map, we are essentially looking at the universe as it was, 380,000 years after the Big Bang, glowing softly across the entire sky. As we drift in this moment of first light, let's absorb how serene it is. The entire cosmos is about 84 million light-years across at this time, a vast sphere of dim, foggy brightness. The temperature of that glow is around 3000 K, akin to the surface of a red dwarf star. But as the eons pass, the light will stretch into colder and colder wavelengths. Today, that same radiation is only 2.7 K, just above absolute zero, manifesting as microwaves. But in this epoch we're visiting, it's a warm illumination, bathing the hydrogen and helium gas that fills space. There are no stars yet, no galaxies, just this afterglow and the gas itself. The scene is peaceful and simple, almost featureless to our eyes. Yet within the slight irregularities of the CMB's glow lie the blueprints of the future universe. Some regions in this afterglow are ever so slightly denser, some slightly hotter or cooler. Differences so small as to be imperceptible except with precise instruments. But gravity is patient and persistent. Given time, those denser spots will draw in more matter and become the birthplaces of the first stars. After the first light shines, the universe enters a quiet, dark age. As odd as it sounds, there is light everywhere, yet no new sources of light. There are not yet any stars to cast beams across space, no galaxies shining in the darkness. The afterglow light itself also grows dimmer and redder as the universe expands, filling space with an ever-softening background glow. For millions upon millions of years, this is how the cosmos remains, transparent, dark to the naked eye, filled with hydrogen and helium gas and a faint, lingering warmth. We call this period the Cosmic Dark Ages. a time of waiting and potential. The term dark here means the absence of stars or bright objects. The CMB light is still around, but it's now so diffuse and low energy that, in visible light terms, everything would look black. If we float through this era, we find it calm and still. The fog has gone, and in its place is clarity, but a darkness cloaked over all, like a starless, eternal night. Yet, within that darkness lies the promise of a new dawn. The gas filling the universe is nearly uniform, but not perfectly so. Here and there, slightly denser clumps of gas exist. Remember those tiny seeds from the earlier fluctuations? In these regions, gravity begins to draw the gas inward ever so gently. Over tens of millions of years, a dance unfolds. Gas clouds contract, heat up, and grow dense at their cores. There is no rush in this process. Gravity works slowly, quietly gathering matter. Imagine drifting through a cold, dark cloud in space and sensing it getting denser and warmer toward the center. These are the first murmurs of what will become stars. Eventually, after about 100 to 200 million years of cosmic time, the darkest era is ready to end. Deep in those dense cores of gas, the conditions become extreme enough for a new kind of light to ignite. Hydrogen atoms slam together under crushing pressure and fuse into helium, releasing radiant energy. At that moment, the first stars are born. Try to envision it. In an expanse that has known only darkness, suddenly a brilliant point of starlight flickers on. And then another, and another, like the first faint stars appearing in the sky at dusk. These newborn stars are not like our sun. They are gigantic, primitive stars, composed almost purely of hydrogen and helium. Scientists believe they were tens or even hundreds of times more massive than the sun, and millions of times brighter. They burn hot and blue-white, pouring energy into the cold surroundings. One by one, these stellar pioneers light up, bringing a gentle sparkle to the once black cosmos. We can imagine looking out at this early universe and seeing a delicate, sparse sprinkle of stars for the first time. The cosmic dark ages are ending. The universe experiences its first dawn, the cosmic dawn. The black veil of night that had stretched for eons is lifted by these first stars' glow. They are isolated and distant from each other, but their combined light begins to softly push back the darkness. Over the next several 100 million years, these stars will gather into the first small galaxies, their gravity drawing together swarms of stars. The once silent universe now starts to hum with activity. Stars live and die, galaxies swirl and merge. But those chapters of the story lie ahead of us. For now, we revel in this moment of transition, the universe transforming from a dark, featureless expanse into one adorned with the light of stars. As part one of our journey gently closes, we have travelled from the birth of the universe to the glimmer of its first starlight. The cosmos has gone from a singular point to a vast expanse, from opaque brilliance to darkness, and now to the faint twinkle of new stars. It's a story of quiet beginnings and patient evolution. We end this chapter gazing at a young universe on the cusp of grandeur. A few infant stars peeking out in a huge sea of night. Breathe softly as you visualize this scene. a sparsely starlit sky where once there was none. In the next part, we will continue our serene exploration, following the formation of stars and galaxies that build on these cosmic origins. Whenever you're ready, we'll drift onward, uncovering how the glittering tapestry of galaxies unfolded from the darkness. Until then, let the calm of the cosmic night keep you company. In the vast darkness of the young cosmos, there was a time with no stars and no galaxies. Only a silent expanse, deep and dark, stretching endlessly in all directions. In that primeval darkness, the cosmos was like a blank canvas, awaiting the first brushstrokes of light. Yet even in this quiet void, something was beginning to happen. Invisible traces of matter were gathering, drawn together by a force as old as time. This was the cosmic dawn before the dawn, the era of darkness before the first light. It is a gentle process, slow and inexorable. Tiny particles drifting through the darkness find one another, pulled by the subtle gravity that each one carries. Over millions upon millions of years, these scattered clouds of gas begin to coalesce. They form larger and larger clumps, like wisps of smoke merging into clouds on a cosmic scale. Within these clouds, deep in their cold and dense hearts, a quiet transformation is underway. After ages of darkness, the first glimmers of light appear in the universe. In the densest pockets of cosmic gas and dust, pressure and heat slowly build. At first, it is imperceptible, a slight warming, a faint glow buried in a swirling cloud. Then, at a moment over 13 billion years ago, the threshold is crossed. Nuclear fusion sparks to life in the core of a forming star, and a new light is born. This is the birth of a star. What was once a cold, dark fragment of a nebula now shines with its own gentle fire. The first generation of stars may have been unlike any we see today. Massive, brilliant, and short-lived. They burned their fuel quickly and lived briefly. They bathed the surrounding space in a soft, newborn glow, pushing back the cosmic night. Their radiance begins to change the universe around them, gently dissolving the primordial mist that once filled space. As this cosmic fog fades away, the darkness yields to clarity, and light can travel freely across vast distances. The era of cosmic dawn gives way to a universe where illumination spreads, linking one star to another across the expanse. Imagine drifting through that epoch, as points of starlight blink into existence around you. The sky that was once perfectly black now glitters faintly with the very first stars. They gather in groups too, forming the seeds of what will become galaxies. In their hearts, these stars are quietly forging new elements, laying the groundwork for planets and life in the far future. From our viewpoint, eons later, we can only envision the serene majesty of these first lights. Each star a beacon, illuminating the void and heralding the next chapter of the cosmos. Stars are still being born, even now, in our universe's hidden corners. Within vast stellar nurseries, giant clouds of gas and dust, new stars take shape continuously. These nurseries are known as nebulae, and they drift through galaxies like gentle, glowing apparitions. One such place is the Orion Nebula, a cradle of star birth, visible from Earth as a hazy patch in the night sky. Inside these nebulous cradles, the story of star formation repeats over and over, an ageless cycle. Picture a nebula, a tapestry of ethereal colours if seen through sensitive eyes, but mostly invisible and dark to human sight. Within it, knots of gas are drawn together. Gravity begins its patient work once more. In some regions, you might find towering pillars of dust and gas, shaped by the winds of nearby newborn stars, standing like silent cosmic monoliths in the gloom. We find ourselves in one such dense knot, a region cool and quiet, hidden from the outside starlight by surrounding clouds. As the gas falls inward, it heats up at the centre. Slowly, a protostar is taking shape, nestled in its dusty cocoon, growing denser and warmer as millennia pass. For a long time, the forming star remains veiled. Only infrared eyes would see a warm, gentle glow deep inside the nebula's obscuring dust. Around the protostar, a disk of gas and dust forms, swirling gracefully like a slowly spinning halo. This disk will one day give birth to planets, moons, and asteroids, a whole system orbiting the newborn sun. But for now, we focus on the star itself, still gathering mass and strength in the quiet shadows. Then comes the moment when the protostar's core grows hot and pressurized enough to ignite fusion. A soft radiance begins to seep through the shroud of the nebula. The cocoon of gas and dust is gently blown back by the newborn star's light and a breeze of particles called the stellar wind. Now, from the darkness of its nursery, a new star emerges and shines out into space. It joins its siblings, perhaps dozens or hundreds born from the same cloud, in a cluster of fresh, young stars. Stars rarely form in isolation. They are born in batches, in clusters that drift together through space. These clusters, over immense spans of time, become the building blocks of galaxies. Gravity, the same gentle force that brought the gas together to form stars, now works on a grander scale. It draws stars toward one another, clustering them by the hundreds, then by the millions, gradually assembling entire galaxies. In the early universe, these gatherings of stars were small and irregular. We might imagine them as tiny islands of light suspended in a sea of darkness. Slowly, they begin to come together, merging in a languid cosmic dance. When two proto-galaxies meet, their stars pass through each other like phantoms. Each star is so distant from its nearest neighbour that direct stellar collisions are exceedingly rare. Yet gravity weaves their paths into one, and the two swarms of stars become a single, larger galaxy over time. Over billions of years, countless stars, clusters, and small proto-galaxies assembled into the grand galaxies we know today. Galaxies grew by absorbing one another, a gradual merging that can last hundreds of millions of years for each encounter. Picture the scene on a colossal timescale. Wispy galactic shapes drawing closer, their stars intermingling, and then slowly settling into a new form together. These ancient mergers were not sudden cataclysms, but slow incorporations, like two clouds blending into one, their shapes changing gently as they unite. During these unions, an invisible hand played a role too. An enormous unseen mass of dark matter surrounding each galaxy helped guide the process, its gravity quietly pulling the galaxies into cosmic communities. Thus, the galaxies were formed and grew, each one an immense congregation of stars bound together by gravity. Over the eons, the number of galaxies multiplied, not a mere handful, but billions upon billions spread across the observable expanse. Some remained modest, with just a few billion stars, faint and dim. Others became giants, containing hundreds of billions of stars in splendid arrangements. In every direction of the sky, there would eventually be galaxies, glimmering like distant lanterns spread throughout the cosmos. The universe that was once dark transformed into a tapestry of light, as the formation of stars gave rise to the formation of galaxies on a grand scale. If we drift closer to these galaxies, we begin to see their shapes and structures. Each galaxy carries a unique design, sculpted by its past and by gravity's guiding hand. Many galaxies settled into graceful spinning disks. From the center of these cosmic whirlpools extend spiral arms, curving outward like delicate swirls of cream in coffee. In these spiral galaxies, like our own Milky Way, new stars still blossom in the dense, cloudy arms, giving them a gentle blue-white sparkle amid the darkness. Other galaxies took on elliptical shapes, giant, glowing ellipsoids of starlight. These elliptical galaxies have no distinct arms. They are more like cosmic snowballs or softly glowing orbs with stars distributed in smooth, featureless halos. They often emerged from galaxies that merged and lost their original structure, the stars dispersing into a broader, blended whole. Elliptical galaxies shine with a warmer, reddish light, full of aging stars, and their star formation has mostly quieted down. They are like ancient cities of light, settled and serene after a bustling youth of starbirth. There are also galaxies of irregular shape, scattered and peculiar, as if still finding their form. These are often smaller, their shapes distorted by the gravitational influence of larger neighbours or by recent bursts of star formation. They hint at how galaxies change over time, constantly influenced by one another and by the events within them. Each irregular galaxy is a reminder of the ongoing, dynamic nature of the cosmos, a gentle chaos that over eons brings forth order, then might loosen into chaos again, only to be reshaped anew. Watching them from a tranquil distance, we sense not true disorder, but the myriad ways gravity and time can sculpt matter into wondrous forms. Floating amid this cosmic ocean of galaxies, one can sense the grand scale of creation. Galaxies gather into clusters, and clusters connect into vast filaments weaving through space, with immense quiet voids between them. In these voids, hardly any galaxies shine at all, only darkness stretching for millions of light years. Along the luminous filaments, by contrast, galaxies are strung like beads on an invisible cosmic thread, outlining the scaffold of the universe. Even on these colossal scales, the process remains gradual and stately. It is a cosmic ballet with billions of performers dancing to the silent music of gravity across the ages. The result is the structure we see in our universe today: stars gathered into galaxies, galaxies into clusters, and clusters into the cosmic web. A masterpiece billions of years in the making. Among all these countless galaxies is one we call home, the Milky Way. Our galaxy is a majestic spiral with sweeping arms and a bright, dense core. It formed from the same processes we have gently explored, born of merging protogalaxies and nourished by steady star formation over eons. For more than 13 billion years, the Milky Way has grown and evolved, shaped by interactions and the lives and deaths of its stars. Within its spiral arms, new stars continue to spark to life, just as countless stars have before them, maintaining an ongoing cosmic legacy. If we could drift far above our galaxy and view it from afar, we would see a pale disk with a faint halo of globular star clusters surrounding it. The spiral arms would be seen as graceful curving trails, rotating slowly about the center, once every few 100 million years. In the core, a gentle golden glow marks where stars crowd together more densely, and at the very center, a sleeping giant, a supermassive black hole, rests quietly. This black hole, millions of times the mass of our Sun, acts as an unseen anchor, its gravity helping to keep the central stars in their cosmic dance. Though it is a place of tremendous gravity, it is not an active menace at this moment, just a heavy, silent presence at the heart of our galaxy, part of the structure, but not disturbing the calm of the vast starry disk. The Milky Way is not alone in space. Dozens of smaller satellite galaxies orbit around it, like fireflies circling a faint lantern. Two of these companions, the large and small Magellanic Clouds, are visible from the southern hemisphere of Earth, appearing as diffuse patches of light in the night sky. They are slowly dancing with our galaxy, and one day they may merge into the Milky Way, adding their stars to our galactic home. Even our nearest large neighbour, the Andromeda Galaxy, is on a gentle collision course with the Milky Way. Yet the word collision belies the grace of the event. It will be a slow embrace taking place billions of years from now, eventually uniting the two into a new, larger galaxy. Within the Milky Way, countless wonders unfold quietly. Stars are born in glowing nebulae. Old stars expand and shed their outer layers like dandelions releasing seeds, enriching the galaxy with heavy elements. Occasionally, a massive star reaches the end of its life in a final outburst, a supernova, scattering material back into space. Even these dramatic events, dispersed over the vastness of space and time, contribute to the calm cycle of cosmic rebirth. Their remnants mix with nebulae, seeding the raw material for new stars and planets, continuing the eternal rhythm of creation and recreation in our galaxy. As inhabitants of this galaxy, we are part of its story. Every atom in our bodies was forged in some ancient star that lived and died long before the Earth took shape. The iron in our blood, the calcium in our bones, the oxygen in our lungs, all were created in stellar furnaces and scattered across space, later to coalesce into our Sun, our planet, and eventually into us. Knowing this, we can feel a profound connection to the stars and galaxies. We are not separate from this cosmic unfolding. We are threads in its immense tapestry, born of stardust and gently glowing with the inherited light of creation. The formation of stars and galaxies is an ongoing, endless story. Even tonight, as we gaze up at the sky, perhaps seeing the gauzy band of the Milky Way on a clear night, new stars are lighting up for the first time in distant nebulae. Galaxies far beyond our own are merging and growing, slowly changing their shapes in dances too slow for any human to perceive in a lifetime. The cosmos continues its gentle unfolding, and with each generation of stars, new possibilities emerge. We live in a universe that is ever evolving yet steadfast in its grand calm, and we continue to learn and marvel at its depth and beauty. We have witnessed how the darkness of the early universe blossomed into starlight, and how stars, gathered into the graceful cities of stars we call galaxies. Our next journey will carry us closer to the lives of stars and the worlds that form around them, as we explore the formation of planetary systems, the children of the stars. In the next part, we will see how the leftover dust and gas around young stars coalesce into planets, and how these distant worlds come to be. In the tranquil aftermath of a star's birth, a broad disk of gas and dust remains swirling around the new sun. This protoplanetary disk is a vast, thin plane of material gradually giving rise to planets. Close to the star, the disk's grains are warmed and glowing. Farther out, in the cool reaches, fine dust and ices collect in shadowy rings. Over time, gentle collisions cause dust motes to stick together, forming clumps that grow into pebbles, then boulders, and eventually embryonic planets. Through countless orbits, these growing bodies sweep up surrounding debris, carving gaps in the disk as they clear their paths. Protoplanetary disks themselves are relatively short-lived on cosmic timescales. Observations suggest they persist for only a few million years before the remaining gas and dust disperse. The young star's radiation and solar wind gradually blow away or heat the leftover material, thinning the disk. Within about 10 million years, most of the primordial disk has vanished, either incorporated into nascent planets or dissipated into space. In some cases, even earlier, strong stellar winds and the pressure of starlight drive out the finest particles. What remains is a newborn planetary system, a young star shining with its family of planets, and perhaps a tenuous debris disk of lingering dust and rock. From afar, astronomers have caught glimpses of these planet-forming disks. For example, the star HL Tauri, only about 1 million years old, is surrounded by a striking protoplanetary disk with multiple concentric rings and gaps. In this ALMA radio image, bright bands of dust alternate with dark lanes, suggesting that infant planets are already clearing pathways in the disk. The presence of such gaps at regular intervals is a silent confirmation of planets in the act of forming, sweeping up material as they orbit. These observations let us witness the formation of planetary systems in real time, revealing the delicate process that sculpted not only HL Tauri's disk, but likely our own solar system's cradle billions of years ago. Eventually, the once opaque disk thins into a faint haze. Young planets settle into their orbits, and the stage of primary construction draws to a close. The star, now a bit more mature, shines more steadily as the chaotic assembly around it calms down. What was a thick cloud of dust and gas is now a set of worlds circling in the starlight. In these early eons, myriad minor bodies, leftover planetesimals and comets, still wander the system, occasionally colliding with planets in great impacts that shape the world's surfaces. But gradually, much of the residual debris is swept up or ejected, and a clearer, quieter planetary system emerges from the dissipating fog. As planets take shape, many end up accompanied by moons, smaller companions orbiting them, born through various gentle processes. In the outer solar system, moons likely coalesced in miniature disks around their parent planets, mirroring the way planets formed around the Sun. Jupiter's 4 largest moons, for instance, may have accreted from a disk of gas and dust encircling the young Jupiter. Other moons may be captured wanderers, stray asteroids snared by a planet's gravity. Mars's tiny moons, Phobos and Deimos, are thought to be captured fragments of the asteroid belt or debris from an impact. And some moons form from giant impacts. In our own solar system, a Mars-sized protoplanet struck the young Earth around 4.5 billion years ago, and the debris from that titanic collision coalesced into our moon. This giant impact hypothesis explains the moon's composition and its relatively large size compared to Earth. It is a dramatic origin story, yet the result is a tranquil presence in our night sky. A moon that has since circled Earth in steady silence. Beyond their origins, moons can play a crucial role in the long-term stability of their planets. Earth's moon, for example, is unusually large relative to our planet, and its gravitational influence help stabilize Earth's rotation axis. Over thousands of years, Earth's tilt only oscillates by a couple of degrees, a regular wobble that contributes to ice ages and Milankovitch cycles, but does not swing wildly. Without the Moon, Earth's axial tilt could vary chaotically. Some models predict it might even wander by tens of degrees or more over long periods. Astronomers have estimated that in the absence of our Moon, Earth's tilt might have fluctuated up toward 85 degrees at times, a drastic change that would drive extreme climate shifts. Instead, thanks to the Moon's steadying tug, our planet's obliquity stays near 23.5 degrees, providing relatively stable seasons over geologic time. This stability is thought to have been beneficial, if not essential, for the development of life under consistent environmental conditions. In contrast, a planet without a substantial moon can experience more erratic changes. Mars, which has only 2 tiny moonlets, undergoes significant variations in its tilt. Geological and computational studies suggest Mars's axial tilt may have swung between near vertical 0 dig and highly inclined, perhaps up to 60 dig, over millions of years. Such large swings could drastically alter a world's climate patterns from era to era. We see evidence on Mars of dramatic climate shifts. For instance, signs that its poles and equator have at times traded places in terms of ice deposition, consistent with a chaotically shifting tilt. While the root causes are complex, the lack of a big stabilizing moon is likely a factor in Mars's restless orientation. By comparison, Earth's big moon has acted as a calming presence, its gravitational pull damping oscillations and ensuring that our planet never leans too far from the vertical. Moons also contribute in other gentle ways. They raise ocean tides, stir a planet's core through tidal flexing, and can even protect the planet by intercepting potential impactors. Jupiter's immense gravity, along with its retinue of moons, serves as a gravitational shield for the inner solar system, deflecting some comets that might otherwise head toward Earth. In many planetary systems, the interplay between a planet and its moons is an ongoing, slow dance of gravitational balance. These silent companions can extend a planet's magnetic field, as Ganymede and Io do for Jupiter, or provide dazzling rings, as the shattered moonlets of Saturn do. But perhaps most importantly, a large moon can impart stability, helping a planet maintain a steady path and orientation as it circles its star. In the dark and quiet of space, a moon's presence can be the difference between a world that's erratic and one that is reliably serene over eons. The planets in a young system do not always stay where they first form. In the early epochs, as planets interact with the remaining disk of gas and with each other's gravity, they begin a slow migration, a wandering journey inward or outward from their birthplaces. Gigantic planets especially can drift through the disk, their gravity tugging on the surrounding gas in a kind of cosmic feedback. Over thousands to millions of years, this process can alter orbits significantly. In our own solar system, for example, Jupiter and Saturn are believed to have migrated substantially in the early days. One intriguing model, called the Grand Tack hypothesis, envisions Jupiter moving inward toward the Sun to roughly where Mars's orbit is today, before reversing course and migrating back outward to its current position. In this scenario, Jupiter's inward trek and subsequent outward tack, when it fell into a resonant dance with Saturn, swept away much of the material that would have formed a super-Earth near the Sun and truncated the disk around 1 AU. This could explain why Mars is smaller than expected, and why the asteroid belt is a region of debris rather than a planet. Such a mellow voyage of a giant planet, spanning vast distances over a gentle timeline, illustrates how dynamic the early solar system might have been. Indeed, in many discovered planetary systems, we find massive planets extraordinarily close to their stars, the so-called hot Jupiters. These are gas giants orbiting nearer to their star than Mercury is to the Sun, often completing an orbit in mere days. Since it's unlikely such huge planets formed in those hot, inner regions, where there was little gas to build them, their presence is strong evidence for migration. They must have formed farther out, where ices and gases were abundant, and then spiraled inward. If Jupiter's migration in our system had not been halted, it might have ended up as a hot Jupiter itself. Instead, interactions with Saturn stopped its inward march. In other systems, no second giant was there to pull it back, so some Jupiter-like planets kept moving inward until the increasing pull of the star or the dissipation of the disk arrested their motion. The result is a hot Jupiter snuggled up to its star, a giant world now locked in a tight, rapid orbit. Remarkably, the very first exoplanet found around a Sun-like star, discovered in 1995, was just such a hot Jupiter, a planet half the mass of Jupiter circling its star in only 4 days, whose presence was revealed by the star's wobble. The discovery was a quiet revolution in our understanding, showing that planetary systems can rearrange themselves in ways we hadn't imagined. Beyond migrations, the gravitational interactions among planets often lead to resonances, harmonic relationships in their orbital periods. In a resonance, planets tug on each other at regular intervals, and if their orbits line up just right, these tugs can stabilize into a repeating pattern. The effect is like a rhythmic, cosmic dance. For example, Jupiter's 3 inner moons, Io, Europa, and Ganymede, are locked in a 1-2-4 resonance. For every 1 orbit Ganymede makes, Europa orbits twice, and Io 4 times, their positions syncing up periodically. This stable resonance keeps their orbits from drifting and also has profound effects, such as driving Io's intense volcanism via tidal energy. Another famous resonance in our solar system is between Neptune and the dwarf planet Pluto. Pluto orbits the Sun twice for every 3 Neptune orbits. This 2-3 resonance ensures that Pluto and Neptune never come close to colliding, despite Pluto's path crossing Neptune's orbit. Pluto is always at a safe distance when Neptune is nearby, a consequence of this gentle gravitational choreography set up early in the solar system's history. Not all resonant interactions lead to serenity. Some can cause instability. If planets or smaller bodies fall into disharmonious resonances, their mutual tugs can pump up orbital eccentricities or change inclinations, eventually leading to close encounters or collisions. Gaps in the asteroid belt, known as Kirkwood gaps, are partially due to unstable resonances with Jupiter. Any asteroid that happens to orbit in those specific periods gets its path perturbed and eventually removed. In young systems, it is thought that as giant planets migrated, they may have swept smaller bodies into unstable resonant orbits, flinging them into the star or out into space. Some may have been sent careening into the inner planets, contributing to heavy bombardment eras that scarred moons and worlds with craters. Yet often, a kind of equilibrium is found. The planets settle into configurations where their gravitational tugs balance out over time. Many exoplanetary systems show multiple planets locked in resonance, indicating they migrated gently into those configurations. A beautiful example is the TRAPPIST-1 system of 7 Earth-sized planets, which exhibits a complex chain of near resonances, maintaining a long-term stability. Similarly, the 4 giant exoplanets orbiting the star HR 8799 appear to be in a 1-2-4-8 resonant pattern. Each planet orbits in roughly double the time of its next inner neighbour. This resonance keeps the massive planets from perturbing each other too strongly, despite their considerable gravity. In this way, What could be gravitational chaos is transformed into a cosmic rhythm. The planets in resonance essentially protect each other's orbits, avoiding close approaches by timing their interactions in a regular cadence. Over billions of years, this gravitational dance continues, usually slow and stately, occasionally punctuated by adjustments if an outside perturbation, like a passing star or a rogue planet, disturbs the balance. But by and large, once a mature planetary system finds its footing, it becomes a quietly evolving architecture, with planets tracing the same ellipses over and over, destined to do so for as long as the star shines. How do we know about these distant planetary systems and their subtle dances? Over the past few decades, astronomers have developed several ingenious, gentle techniques to detect exoplanets, planets orbiting other stars, without ever seeing them directly with our eyes. Each method is a sensitive listening or watching for the faint whispers a planet makes amid the star's brilliance. One fruitful approach is the radial velocity method, often described as detecting the star's wobble. As a planet orbits a star, their mutual gravity causes the star to move in a tiny orbit as well, teetering around the system's center of mass. To us, this motion appears as the star moving slightly towards and then away from Earth in a regular cycle. By using high-precision spectrographs, astronomers can detect minute shifts in the star's spectrum, the Doppler shift, as the star's light is stretched to red when it moves away and squeezed to blue when it moves toward us. The effect is incredibly small. For example, Jupiter causes the Sun to move at about 13 milliseconds and Earth only about 0.1 milliseconds, which is almost imperceptible. Modern instruments, however, can measure velocity changes of just a few milliseconds or even less, which allows the detection of sizable planets tugging on nearby stars. In 1995, this method yielded the first confirmation of an exoplanet around a Sun-like star. 51 Pegasi's subtle wobble revealed a hot Jupiter in a 4-day orbit. Since then, radial velocity surveys have calmly uncovered hundreds of planets, from massive Jupiter-like worlds down to planets only a few times heavier than Earth, by patiently observing the periodic shifts in starlight over months and years. Another highly productive technique is transit photometry, which watches for tiny dips in a star's brightness when a planet passes directly in front of the star. If the alignment is just right from our vantage point, a planet will transit its star once every orbit, momentarily blocking a small portion of the star's light. The drop in brightness is usually incredibly small. An Earth-sized planet transiting a Sun-like star might dim the starlight by only 0.008%, a barely perceptible blink. Larger planets cause a deeper dip. For instance, a gas giant might dim a star by 1% or more. By continuously monitoring stars for these rhythmic dimmings, missions like Kepler have discovered thousands of exoplanets. The transit appears as a smooth, shallow decline in brightness for a few hours, then a return to normal, a gentle heartbeat in the light curve of the star. From these light patterns, astronomers can infer the planet's size, larger planet, larger dip, and its orbital period, time between dips. When combined with radial velocity or other data, the planet's density can be estimated, hinting at whether it's gaseous or rocky. Transit observations have even allowed us to detect wisps of atmospheres on some exoplanets by analyzing starlight filtering through during the eclipse. It's a delicate and sensitive method, the equivalent of detecting the shadow of a tiny moth passing in front of a distant lighthouse lamp. And yet, with modern detectors and careful analysis, it has become the most prolific way of finding new worlds beyond our solar system. Other methods add to our knowledge in more specialized situations. Direct imaging of exoplanets is challenging because a star's glare is overwhelmingly bright compared to any orbiting planet. Still, using advanced optics and techniques like coronagraphs to mask the star, astronomers have directly photographed a few dozen exoplanets, typically young massive ones far from their stars. These tend to be planets several times the mass of Jupiter, orbiting at wide separations, tens of astronomical units or more, and often still warm from their formation, glowing in infrared light. In such cases, the faint point of light from the planet can be picked out next to the blocked-out star. One famous success is the HR 8799 system, where 4 giant planets were imaged orbiting a young star, appearing as tiny specks of light in the darkness, moving slightly over years of observation. Direct imaging is like looking at fireflies dancing around a distant searchlight. It requires extreme patience and technology, but it provides actual pictures of these distant worlds and their orbits. Meanwhile, the gravitational microlensing technique exploits rare cosmic alignments. If a foreground star happens to pass almost directly in front of a background star from our viewpoint, the foreground star's gravity acts as a lens, magnifying the background star's light for days or weeks. If that foreground star has a planet, the planet's gravity adds a brief extra blip or alteration in the light curve during the event. By monitoring dense star fields in the Milky Way bulge, projects have captured such microlensing events, thereby inferring the presence of planets that might be thousands of light years away, including some that are not bound to any star, so-called free-floating planets. Microlensing is a transient, one-time signal. Once the alignment is gone, it will never repeat. But it can detect planets of Earth mass, or even smaller, at vast distances. It's a method that has revealed a few dozen planets, complementing the more nearby discoveries of transits and radial velocity. Lastly, there is astrometry, the oldest hoped-for method, precisely measuring a star's position on the sky to see the tiny corkscrew motion caused by orbiting planets. This requires extraordinary precision, micro-arcseconds, something recently made possible by space observatories like Gaia. While astrometry has not yet confirmed many planets, it is expected to enrich our census, especially for massive planets in wider orbits, where the star's wobble on the sky plane is largest. Together, these techniques weave a fuller picture. Radial velocity listens to the tug of a planet. Transits watch its shadow. Direct imaging tries to glimpse its glow, and microlensing catches its gravitational signature. Each method is subtle and requires a patient eye, a testament to the calm persistence of astronomers untangling faint clues from the vast silence of space. Through these methods, over 5,000 exoplanets have been confirmed to date, and we now know that planets are incredibly common. Astronomically speaking, most stars have their own family of planets. In fact, studies of transit data from the Kepler telescope imply there are likely more planets than stars in our galaxy, meaning planets are abundant, from the smallest rocks to gas giants, orbiting all manner of stars. Our once solitary concept of a solar system has expanded into a universe teeming with planetary systems. Each new planetary system discovered offers a gentle revelation about the variety of worlds nature can produce. Some systems remind us of our own solar system, with multiple planets in comfortable, near-circular orbits around a stable star. But many are startlingly different, though we describe them in measured, curious tones rather than alarm. For there is wonder, but not fear, in these differences. One of the most intriguing findings is that planet types common in the galaxy are absent in our solar system. For instance, many stars host planets known as super-Earths or mini-Neptunes. worlds larger than Earth, but smaller than Neptune. These planets, ranging perhaps 2 to 4 times Earth's diameter, appear to be extremely common in our galaxy. Yet our Sun has no such planet. There is a gap between Earth and the next larger planet, Neptune, with nothing in between. The prevalence of super-Earths suggests that whatever processes build planets often make ones in that intermediate size, range with thick atmospheres or vast oceans. Their absence in our system is a curiosity, perhaps due to Jupiter's disruptive influence early on, or maybe just a quirk of how our particular disk evolved. In any case, the universe has no shortage of these mid-sized worlds, showing that planetary systems come in many flavors, and ours is just one specific case. Likewise, the arrangement of planets can defy what we once assumed was a natural order. Our solar system's giant planets reside in the cold outer zones. But we've found systems where giants crowd blisteringly close to their star. The first exoplanet discovered around a Sun-like star, 51 Pegasi b, revealed such an arrangement. A Jupiter-mass planet practically hugging its star. At the time, it was a surprise, but now we know hot Jupiters are relatively uncommon. Perhaps a few % of stars have them, yet utterly real. Conversely, compact systems of rocky planets are also found. A beautiful example is TRAPPIST-1, a dim red dwarf star with 7 known planets, all of which are roughly Earth-sized and packed in orbits that would fit well within Mercury's orbit. They circle their cool star in periods ranging from about 1.5 to 19 days. Despite the tight spacing, the TRAPPIST-1 planets have a resonant harmony that likely keeps them stable over long times. Neighboring planets in that system are locked into rhythmical orbital period ratios near 8.5, 5.3, 3.2, etc., ensuring that their gravitational tugs on each other repeat in patterns that avoid conflict. It's an extraordinary configuration, 7 small worlds sitting side by side in the glow of a tiny star. The TRAPPIST-1 system offers a glimpse of planetary diversity in the galaxy. All 7 of its known planets are Earth-sized and terrestrial, packed closely around an ultra-cool dwarf star. In this artist's illustration, the 7 worlds are shown together against a backdrop of stars, each orb somewhat different in hue and texture. They are imagined as a family of varied terrestrial planets, some perhaps arid and cratered, others possibly cloaked in clouds or oceans, all orbiting their faint red sun in tight formation. Their star is so cool and dim that despite the planet's proximity, several lie in the star's habitable zone, where temperatures could allow liquid water. From the perspective of TRAPPIST-1, the constellations we know, like Orion, faintly visible in the background, appear slightly distorted, a reminder that these planets are real places in our galaxy under the same wider sky, just with a different sky view. TRAPPIST-1's discovery broadened our perspective on how planetary systems can look. Not only can small stars have multiple Earth-like planets, but those planets can interact gravitationally in gentle resonance, orbiting in days, yet remaining in stable alignment. It's a quiet clockwork of planets, more tightly packed but surprisingly orderly compared to our solar system. Other systems show different extremes. The star HR 8799, much more massive and luminous than the Sun, hosts 4 giant planets each several times heavier than Jupiter. Unlike TRAPPIST-1's compact configuration, these giants sprawl far from their star. Even the innermost is beyond where Neptune orbits in our system. Astronomers have directly imaged this system, watching the 4 points of light move in their wide orbits over years. Intriguingly, those massive planets seem to orbit in resonance as well, a 1-2-4-8 sequence, hinting they migrated into a balanced gravitational arrangement. In contrast to the warm hues of Trappist's illustration, the HR 8799 images come to us as faint, ghostly dots in infrared against black space, emphasizing how far and cold those planets are. Yet they too form a family, likely with their own moons and rings, circling a bright young star that is a neighbour of 51 Pegasi in the constellation Pegasus. It's sobering and serene to realize that planetary systems can be gigantic and spacious or tiny and compact, all following the same basic physics of gravity and motion. Even our nearest stellar neighbours harbour planets. In 2016, astronomers confirmed a planet orbiting Proxima Centauri, the closest star to the Sun, only 4.2 light-years away. This planet, Proxima b, is at least as massive as Earth and orbits within the star's habitable zone, where temperatures might allow liquid water on its surface. Though Proxima Centauri is a small red dwarf emitting a dim, reddish light, its planet receives enough warmth to be potentially Earth-like in climate. The discovery of Proxima b was a gentle revelation that the nearest possible new world is indeed there, circling right next door in cosmic terms. It underscored that planets truly are everywhere. Even the star that is essentially our next-door neighbour in the galaxy has a planet that could be somewhat similar to our own. And Proxima is not unique. The other stars in the Alpha Centauri trio might also have planets, and many nearby sun-like stars do as well. As we look up at the night sky, nearly every star we see, and countless we cannot see, likely hosts planets, some gas giants, some rocky, some in between. There is a quiet universality in this knowledge. The formation of planets is a natural part of star formation, happening throughout the Milky Way. Comparing these systems to our solar system, we find we are in one sense ordinary. We orbit a typical middle-aged star with a mix of rocky inner planets and outer gas giants. But in other senses, our system might be a somewhat rare arrangement. We lack super-Earths, our giant planets stayed far out, and we have that big stabilizing moon. Yet the differences are just variations on common themes. The physics that shaped our system is at work everywhere. Disks forming planets, planets capturing moons, migrations and resonances sculpting orbital layouts. In some stars' entourages, we see mirrored aspects of our own history, and in others, entirely new patterns that our theories must account for. All of these planetary systems, whether familiar or exotic, share the same gentle cosmic origin. Born from stardust, guided by gravity into diverse architectures. They remind us that our night sky's mystery includes not just stars, but a multitude of unseen worlds circling them, each with its own story. As we conclude this part of our journey, we reflect on the formation of planetary systems as a calm yet profoundly creative process in the cosmos. From swirling disks of dust to the intricate clockwork of mature orbits, the evolution is gradual and majestic, full of subtleties. In the next part, we will continue our exploration of the cosmos's grand narrative. Gently, our voyage will carry us onward, inviting us to delve even deeper into the quiet wonders of space. A soft step further on our path through the stars, with the same calm curiosity guiding us forward. Let us now quietly venture to the next chapter of this odyssey, carrying with us the understanding that every point of light in the sky could be a sun to its own family of worlds, formed in the elegant dance we have just described. We proceed, in peace and wonder, to part 4, eager to uncover the next secret the universe will reveal, yet doing so in the same restful and contemplative spirit. High above in the silent void of space, our home planet drifts into view. A delicate blue sphere floats against a backdrop of endless darkness, swirled with white clouds and deep turquoise seas. From this peaceful vantage, Earth appears calm and borderless, a single living world suspended in stillness. There is no sound up here, only the quiet glow of the planet below, a serene jewel shining softly in the cosmic night. In this gentle view from the silence of space, we begin to sense the profound beauty and unity of Earth. In the early days of space exploration, humanity's first fragile footsteps beyond Earth brought newfound perspective. The first orbital eyes were not human, but mechanical, simple satellites that carried cameras into the sky. In 1959, a tiny satellite named Explorer 6 beamed back a faint, grainy image of Earth from orbit. It was a blurred glimpse, just a portion of the sunlit Pacific Ocean and its cloud cover. Yet it marked the dawn of seeing ourselves from above. Soon after, in 1960, the Tyros-1 weather satellite sent down the first television pictures of Earth's swirling cloud patterns, revealing the planet's dynamic atmosphere in motion. These early images were monochrome and low detail, but to those watching on the ground, they were wondrous. For the first time, we looked down upon our own world from the outside, witnessing Earth as a whole rather than as separate places. Even before humans ventured into orbit, these mechanical observers quietly paved the way. They showed swirling storms from above and the bright reflection of sunlight on clouds and oceans. The concept of Earth as one single orb was no longer theoretical. We could finally see it. Each early satellite that opened its unblinking eye provided a gentle preview of what astronauts would later experience in person. As these first orbital eyes gazed down, humanity gained a soft awakening to our planet's grand but fragile presence against the vastness of space. With the success of those initial satellites, we soon learned the value of observing Earth's weather from space. In the silence of orbit, weather systems unfold in slow, mesmerizing dances across continents and oceans. By the mid-1960s, new satellites hovered high above the equator in geostationary orbit, keeping constant watch on the hemisphere below. From their perch, tens of thousands of kilometers away, they could see an entire face of Earth at once, an entire disk swirled with cloud tendrils and storm cyclones. For the first time, meteorologists could observe a hurricane's swirling arms stretching over oceans, or watch a winter storm blanket a whole continent, all in real time. The weather, once local and unpredictable, became a global ballet that we observed quietly from above. These orbiting sentinels transmitted images at a leisurely pace, one frame at a time, giving a calm, continuous view of Earth's cloud layers and weather patterns. On Earth, someone could look at a screen and see day turn to night across half the globe, the Terminator line, a gentle curve of shadow sweeping across the surface. They could follow the slow drift of clouds, the growth of a tropical storm, or the gradual shifting of seasons. The perspective from space brought context. A small storm over a town was part of a greater tapestry of clouds tracing the planet's atmospheric currents. This soft, global viewpoint helped humans understand the weather in a new way, seeing connections between what happens over distant oceans and the rainfall at home. In the calm imagery from above, the chaos of weather found pattern and form, allowing forecasters to warn and prepare, and everyone to appreciate the artistry of our planet's atmosphere. As the decades went by, our ability to observe Earth from space became ever more advanced. By the late 20th century, a fleet of satellites quietly circled the planet, each with a dedicated mission. Some orbit from pole to pole, scanning every part of Earth as it rotates beneath. Others hang high above the equator in geostationary orbits, appearing to hover over the same spot and constantly watching a full hemisphere. Together, they form a global observatory, a peaceful armada of sentinels drifting through the silence of space, continuously monitoring Earth's pulse. These satellites observe our planet in many different ways beyond ordinary pictures. They measure the color of the oceans to reveal plankton blooms and the productivity of the seas. They detect the heat radiating from land and clouds to map temperatures and track moisture. Radar-eyed satellites peer through clouds to chart rainfall and changes on Earth's surface, day or night. Each spacecraft moves swiftly along its path, yet provides a steady stream of data. Together they give us an unbroken, calm record of Earth's changing conditions, allowing scientists to study our planet's climate, weather, and environments with unprecedented detail. In addition to these automated watchers, astronauts aboard the International Space Station join in observing our home from above. Circling the globe every 90 minutes, they witness as many as 16 sunrises and sunsets each day. Often they press cameras to the windows, capturing images of swirling hurricanes, erupting volcanoes, or simply the breathtaking colors of Earth's landscapes far below. With each orbit, they see familiar patterns, coastlines, islands, and cloud formations, yet always with subtle differences. A new spiral in a storm system, a fresh dusting of snow on a mountain range, or the changing hues of a season sweeping across continents. This ever-changing panorama reinforces how alive and dynamic our world truly is. Through the combined eyes of our machines and our fellow humans in orbit, we maintain a gentle but vigilant watch over the planet we call home. Perhaps the most iconic view of Earth from space came from human eyes during the Apollo era. In December 1968, the Apollo 8 mission took astronauts around the moon, and as they emerged from behind our lunar neighbor, they were greeted with an astonishing sight: Earth rising over the moon's grey horizon. One of the crew snapped a photograph known as Earthrise, capturing our blue planet adrift in the black cosmos above the moon's surface. In that image, Earth is a small, radiant sphere, beautiful, isolated, fragile. This unexpected view stirred something deep in all who saw it. It was as if humanity, for the first time, saw itself in a mirror hanging in space. A few years later, in 1972, Apollo 17 astronauts took another famous photograph, now simply called the Blue Marble. This time, the crew, traveling between the Earth and Moon, looked back and saw the fully illuminated disk of Earth. The sun was directly behind them, lighting up our planet in its entirety. They captured Earth in rich color, swirls of white clouds, expanses of blue ocean, the ochre shades of deserts and continents, and the dazzling white of Antarctica at the bottom. Against the pitch-black void, Earth appeared as a marble of blue and white glass. The image was breathtaking in its clarity and wholeness. No continents were cut off, no part of the globe in darkness. It was a complete portrait of our world in one frame. These images resonated deeply with people on the ground. Many who viewed the Earthrise and Blue Marble photographs felt a sudden clarity about our place in the universe. Here was all of humanity, all of history and life, contained on a single sphere floating in emptiness. National boundaries were invisible. Only nature's vast patterns were evident. Such views helped spark a growing awareness of Earth's unity and vulnerability. They contributed to the environmental movement as people realized how finite and precious our planet appears when seen from space. The perspective was gentle yet profound. We are the caretakers of this bright, lonely marble. It is the only home we have. Seen from space, Earth's atmosphere appears as a thin, glowing halo around the planet's edge. At orbital sunrise or sunset, a delicate band of blue and gold encircles the world. This slender veil is all that protects life below. Astronauts are awed by how narrow and fragile this layer is. A tenuous bubble shielding the surface from the void. Most of the time, the atmosphere is nearly invisible from orbit, just a faint haze hugging the planet. But when the sun's light angles through it, the air ignites into layers of colour, deep indigo near the dark Earth, fading to pale blue, and then to the black of space. In those moments, one can literally see our air glowing softly. Often, a flicker of distant lightning will silently light up a cloud deck, or the aurora's gentle ribbons will ripple near the poles. These subtle lights at the edge of the atmosphere remind the observer that, though Earth looks tranquil from here, its sky is alive with activity. From space, we also keep careful watch on this vital layer. Specialized satellites track the atmosphere's composition, detecting changes in ozone, greenhouse gases, and other elements. By looking down from above, scientists discovered the thinning of the ozone layer decades ago, a warning only visible from a global perspective, and humanity responded to help mend that protective shield. Observing the atmosphere as a whole, we also see patterns like jet streams snaking around the planet, and even thin veils of ash that encircle the globe after a large volcanic eruption. The view from space teaches us that our atmosphere, visible as that faint blue line, connects and sustains all life below. It is delicate, yet it is our shield. From the quiet altitude of orbit, Earth's surface unfolds in a mosaic of blues, greens, and whites. The vast oceans dominate the view, covering most of the globe in deep blue that fades to turquoise near sunlit coasts. At times, delicate swirls of pale green emerge in the sea, great blooms of plankton floating on currents, visible even from space as a gentle signature of life. Across the planet, bands of cloud often trace the boundaries between air and water, casting soft shadows on the ocean below. The continents present broad strokes of colour and texture. Golden deserts stretch across large expanses, while dense forests form dark emerald patches in the tropics. Grasslands and farmlands create a subtle patchwork of lighter greens and browns, a pattern that shifts through the seasons. Snowy mountains and polar ice caps gleam bright white, their forms growing and receding with winter and summer. With each passing month, the land changes slightly. Forests deepen in green, fields turn from brown to gold, showing the pulse of life and climate across Earth's face. When night falls on the earth below, a different portrait appears. The land is dotted with faint glimmers of light, where cities come alive in the darkness. These city lights twinkle gently, outlining coastlines and shining like tiny constellations on the planet's night side. Occasional flashes of lightning illuminate the tops of clouds, silently flickering as storms move over the surface. And near the poles, the aurora's ghostly glow ripples in curtains of green and red light, a quiet celestial dance at the edge of space. The night side of Earth, observed from orbit, is calm and enchanting, an almost sleeping world marked by scattered lights and natural glow, all beneath the canopy of stars that stretch above our fragile planet. Astronauts often describe a profound shift in perspective when they gaze down at the entire Earth from space. In the stillness of orbit, they see a world with no divisions, just one glowing planet rotating slowly below. Borders and distinctions that seem important on the ground fade away against the backdrop of this unity. A deep sense of awe and humility washes over them. Many have been moved to tears by the sheer beauty of Earth floating in the void, and by a sudden, powerful feeling of connection to all of humanity and life. From their lofty vantage point, astronauts witness scenes that stay with them forever. The razor-thin blue aura of atmosphere hugging the planet, the brilliant reflection of sunlight on vast oceans, and the soft dance of the auroras at the poles. They frequently remark on how small and precious Earth looks, a bright blue oasis amid the darkness of space, isolated yet alive. In those moments, they realize how vital it is that we all work together to protect this shared home. The overview effect is not a loud or jarring epiphany, but a gentle, dawning awareness that forever changes one's perspective. It is the realization that all people and all places are connected, crewmates sharing a tiny, beautiful world. This change in viewpoint does not remain with the astronauts alone. It has spread through the stories and images they bring back. Each photograph of Earth from space, each live video of our planet slowly turning, gives those of us on the ground a small taste of that experience. We are gently reminded that our differences mean little compared to what we share. The same oceans, the same atmosphere, the same fragile planet. This calm, unifying realization that we are all part of one Earth is one of the greatest gifts of venturing beyond our world. Viewing Earth from space reveals many subtle connections that bind the planet's systems together. From above, one can see how an event in one region can have effects far away. For example, a dust storm in the Sahara can drift across the ocean and settle over the Amazon, nourishing that distant rainforest with fine mineral sand. Likewise, a warm Pacific Ocean current known as El Niño can shift weather patterns on multiple continents at once. No part of our planet truly exists in isolation. The atmosphere, oceans, land, and life all interact in a delicate balance as one connected Earth system. This interconnectedness also highlights the planet's fragility. Over decades, satellites have watched polar ice caps and mountain glaciers gradually recede, while ecosystems on land subtly shift and change. In some regions, forests and grasslands have slowly given way to expanding desert. In others, barren areas have turned green with new growth. These changes are often so slow and subtle that they are hard to notice from the ground, but they become clear when we compare years of images from space. Like tending a garden from above, we can observe where our planet flourishes and where it struggles. These gentle yet persistent observations remind us that Earth is alive and changing, and that it needs thoughtful care. Yet even in its fragility, Earth shows a capacity for renewal. We have witnessed forests regrow after fires and clearings, and the ozone layer gradually healing after we curtailed the chemicals that harmed it. These quiet successes, visible from space, offer hope and illustrate that our actions can make a positive difference. The calm, continuous watch from orbit not only warns us of problems, but also reveals nature's resilience when given a chance to recover. Above all, seeing our planet as one whole reinforces that this pale blue dot is the only home we have. A solitary oasis of life, adrift in the darkness of space. Our fates are woven together as tightly as the clouds and currents we observe from above. This perspective inspires us to cherish and protect our fragile, interconnected home. As we conclude our gentle gaze upon Earth from the silent heights of space, we carry forward a renewed sense of wonder and guardianship for our fragile planet. The sight of the whole Earth, tranquil, radiant, and alive, lingers in our minds like a calming melody. With this perspective in our hearts, we are ready to drift onward. In the next part of our journey, we will venture farther out beyond our home world, still guided by the peaceful curiosity that has carried us this far. The cosmos awaits, vast and mysterious, and we continue our exploration with the same gentle awe, knowing that our precious Earth, glowing blue in the darkness, will always be our point of origin and our place of return. Until then, we float in the quiet of space, inviting you to rest in this calm as Earth's soft light fades slowly behind us. Our journey now turns to the moon, a familiar face in the night sky, and yet a world of quiet mystery. For as long as humans have gazed upward, the moon has been a constant, gentle presence, Earth's silent companion. In the stillness of midnight, it hangs suspended, bathed in silver light, watching over our world. In this part of our cosmic odyssey, we explore the moon's story, from its fiery birth to its tranquil glow, from the subtle pull it exerts on our planet to the inspiration it has stirred in our hearts. Each step will be taken softly, as if walking on lunar dust, uncovering the moon's secrets in a calm and soothing light. Billions of years ago, in the early dawn of the solar system, the moon's journey began. Scientists believe that the moon was born from a colossal event when a young Earth and a wandering planetesimal collided. In that ancient collision, molten debris was cast into Earth's orbit, gradually coalescing under gravity. Over time, this ring of glowing debris cooled and gathered into a single sphere, our moon. Though its origin was touched by cosmic turmoil, what emerged was a quiet companion. The newborn moon glowed red-hot against the darkness, but it gradually cooled and solidified into a quiet, solid world. As eons passed, its surface froze into stillness, preserving the memory of its fiery birth in what became a peaceful orb. From the beginning, Earth and Moon were locked in a gravitational dance. The moon's rotation gradually slowed as Earth's pull tugged on it, until it became tidally locked, one face of the moon forever turned toward Earth. This meant that from our planet, people would only ever see the moon's near side, its familiar face, while the far side remained hidden in mystery. The locked gaze between Earth and Moon was established, a bond that would shape both of their futures, gently over the ages. The surface of the moon today is like a vast, silent tapestry of history. Without air or weather to wear it away, every event that ever scarred the lunar ground remains recorded in the dust and rock. Ancient asteroid impacts pockmarked the surface with craters large and small. Some are mere speckles, others vast basins hundreds of kilometers across. In the moon's youth, some of these basins filled with dark lava that cooled into smooth plains. Early sky watchers mistook these dark patches for seas and gave them poetic names: the Sea of Serenity and the Sea of Tranquility. In truth, they are dry plains of basalt, but the names capture their quiet, otherworldly beauty. Wandering over this landscape in our imagination, we can sense the stillness. Towering crater rims cast long shadows at lunar sunrise and sunset, while their centers lie in deep darkness. On the lunar day side, the ground is bathed in bright sunlight, and the grey dust gleams. But around every shadow there is utter silence. The moon has no atmosphere, no breeze, no sound. If you were standing there, your footsteps would fall without a sound, and the fine powdery dust would hang briefly and then settle, to remain undisturbed for perhaps millions of years. Every footprint, every trace of exploration is preserved in this frozen tableau. The landscape is stark, yet serene, illuminated by a sun unfiltered by any air. This is a world where time nearly stands still, and each feature on the surface whispers of an ancient past. Yet amid these grey highlands and dark plains, one might think the moon is completely changeless. Indeed, it is often called a dead world, geologically quiet for billions of years. Yet in its stillness there is subtle change. Micrometeorites constantly pepper the surface, faintly reshaping the dust. Now and then a larger rock from space strikes, carving a new crater in an instant, yet even that arrives without a sound. But most of the time, the moon simply watches Earth, its face gently lit and dimmed by the angle of sunlight, a serene witness to the passage of time. Though the moon hangs quiet and distant, its influence reaches every shore of Earth. Across our planet, the oceans respond to the moon's gravitational pull, rising and falling in ceaseless rhythm. Each day, in an ancient dance, the sea draws up toward the moon's presence and then releases, creating the tides. Imagine the waterline on a calm beach moving in and out, a whispering pulse guided by the moon overhead. This gentle tug between Earth and moon has been going on for eons, shaping coastlines, nurturing life in tidal pools, and reminding us of our connection to our silent satellite. The effect is subtle but persistent. When the moon is overhead, or on the opposite side of Earth, its gravity ever so slightly draws the ocean toward it, causing a high tide. Between those areas, the water is pulled less, causing low tides. The entire planet's water envelope shifts in response, a global breathing synchronized with the moon's motion. The sun contributes its gravity to this mix, but being much farther away, its pull is gentler. The moon's nearness makes its effect dominant, guiding the primary rhythm of 2 high tides and 2 low tides each day. This cycle is steady and reliable, a cosmic clock that coastal life has long tuned itself to. Countless sea creatures live by the rhythm of the tides, as if the moon is silently conducting an oceanic lullaby. Over billions of years, the moon's tug has quietly altered Earth's motions. Tidal friction from the moon's pull has slowed Earth's rotation, making our days a little longer over time. As a result, the moon drifts a few centimeters farther from Earth each year, as if giving us more space. The moon's gravity also keeps Earth's tilt stable, like an anchor that prevents wild climate swings. Without our lunar stabilizer, Earth might wobble, and the seasons could change unpredictably. In its quiet way, the moon has helped keep Earth a gentle and habitable home, maintaining our planet's rhythm and balance. Each night, if we watch the sky carefully, we notice the moon changing shape. These changes are the moon's phases. a gentle cycle of light and shadow that repeats every month. Like the slow breathing of the sky, the moon waxes to full brightness and then wanes back to darkness with comforting regularity. It begins as a thin crescent low in the twilight, a delicate silver sliver in the twilight sky. Night after night the crescent grows, first to a half-illuminated first quarter, then to a swelling gibbous phase, until the full moon rises, round and radiant, bathing the landscape in a soft, pale glow. After full, it recedes again, waning through gibbous to last quarter, then to a thinning crescent at dawn, and finally to new moon, when it disappears into the sun's glare and the cycle begins anew. These phases are caused by the moon's journey around Earth, with sunlight illuminating different portions of the side we see. Yet to early humans, they must have seemed like magic. The moon transforming its shape over the weeks, never the same 2 nights in a row, yet always returning to its full glory after a fixed interval. In a time before artificial light, the moon's phases were a vital clock in the sky. The bright nights of a full moon made it easier to hunt or travel. The dark nights around the new moon revealed the stars in all their glory, perhaps inspiring stories and wonder. Many early calendars were lunar, counting months by the moon's cycle. Even the word month comes from the moon. Long before we knew the moon's true nature, it lived in our imaginations. Ancient cultures wove myths and legends around this glowing orb. Some saw a deity in the moon, perhaps a goddess of night or a god guiding the hunt. Others saw animals or faces in its pale markings, a face peering down, or a rabbit silently keeping divine company. The moon's gentle light was woven into beliefs about love, fertility, and the rhythms of life. It served as a guide for night travelers, a companion in the darkest hours. Through stories and songs, people tried to explain the moon's changing phases and its mysterious influence on earthly life. These early interpretations, though not scientific, show how deeply the moon touched the human spirit. As curiosity grew, so did our effort to understand the moon's true nature. But it was not until the invention of the telescope that the moon's secrets truly began to unfold. In 1609, Galileo Galilei pointed a simple telescope at the moon and was astonished by what he saw. The moon was not a smooth, perfect heavenly disk as many had thought, but a rugged world. He sketched dark plains and bright highlands, noticing that the play of sunlight and shadow revealed mountains and craters. This revelation changed our perception of the moon from a mystical light in the sky to a place, a world with its own geography. In the centuries that followed, telescopes improved, and astronomers mapped the moon in detail. They gave names to craters and regions, often the names of famous observers, philosophers, and the poetic seas imagined long ago. Each feature charted was another step towards seeing the moon as a neighbouring world rather than just a distant light. By the 19th and 20th centuries, detailed lunar maps existed, and people were dreaming of actually visiting. Writers imagined fantastic voyages to the moon, and artists painted its stark, alien landscapes. The moon continued to inspire both scientific inquiry and creative imagination, bridging the gap between knowledge and wonder. For millennia, the moon remained out of reach. That changed in the 1960s with the dawn of space exploration. The first robotic probes managed to touch the moon and send back glimpses of its surface, preparing the way. Then, In July 1969, human beings at last set foot on the moon. Apollo 11 carried astronauts Neil Armstrong and Buzz Aldrin to the Sea of Tranquility, one of the moon's lava plains with a name befitting the moment. Armstrong's first step onto the dusty surface was taken slowly and carefully. In the airless silence, his boot pressed into fine grey soil, leaving a footprint that still lies undisturbed. One small step for a man, one giant leap for mankind, he called back to Earth. Words heard by millions, yet out on the moon's surface, there was only stillness. Over the next few years, a handful of Apollo missions followed, and more astronauts walked on the moon. They collected rocks and gazed back at the distant Earth hanging in the black sky. They found the moon barren and silent, but also magnificent. The astronauts often spoke of the profound quiet and desolation, coupled with the awe of standing on another world. Those brief visits left more than footprints. The astronauts brought back samples of lunar rock and soil that scientists eagerly studied. These samples confirmed the moon's great age and its kinship with Earth, supporting the idea that the moon was born from Earth's own materials long ago. Touching the moon had given us not only tangible pieces of another world, but also a new perspective on our own. Human exploration of the moon paused after 1972, and no one has walked there since. But the moon was by no means forgotten. Spacecraft from various countries continued to orbit and study our lunar neighbour, mapping it in high detail, and even looking for hidden ice in the moon's perpetually shadowed craters. Each new observation adds to our picture of this familiar, yet still mysterious world. And always, on clear nights, people still step outside, look up, and find the moon. Perhaps feeling a quiet connection to those who journeyed there, and to the wonder of what lies beyond our own world. Throughout history and into the present, the moon has cast a gentle influence not just on our planet, but on human imagination, science, and technology. It has often been a muse. Poets have written about the moon's glow on a lover's face. Painters have tried to capture its silvery luminescence on canvas. Musicians have composed lullabies and nocturnes to celebrate the moon's gentle light. In literature and art, the moon has long been a symbol of romance, mystery, and even melancholy. In the modern world, it still appears in our stories and films as a source of wonder, its gentle presence offering a sense of comfort that transcends cultures and time. For scientists, the moon has been a gateway to understanding the wider cosmos. Studying the moon's countless craters and its composition has revealed the early history of our solar system. A record of ancient impacts preserved on the airless moon that has long been erased from Earth's active surface. The moon's predictable orbit around Earth helped early astronomers discern the laws of gravity and the mechanics of celestial motion. By observing how the moon moves and influences Earth, we refined our understanding of orbital mechanics and tides. In these ways, our silent companion has quietly furthered human knowledge. The effort to reach the moon also spurred great advances in technology. To send people safely to the lunar surface and back, we had to invent new materials, build compact computers, and develop precise navigation techniques. The Apollo program led to innovations in computing that trickled down into everyday technology in subsequent decades. The moon, by challenging us to go beyond our limits, has indirectly shaped our technological world. And yet, one of the moon's greatest influences might be what it symbolizes. It stands as a reminder of what humanity can achieve when we dream beyond our immediate horizon. At the same time, its tranquil, unchanging face reminds us to be humble and reflective. For those who have stood on the moon and gazed back at Earth, the experience brought a profound sense of connectedness and contemplation. They saw our home as a fragile blue marble against the vast darkness, a perspective that fostered a new awareness of our shared home and its fragility. In this way, the moon not only pulls on our oceans, but also on our hearts and minds, gently guiding us to wonder, to learn, and to aspire. The moon, in all its quiet glory, continues to accompany us through our nights and through the ages. Its soft light has eased the human fear of darkness, and its cycles have given us a way to mark time and change. From the time of our earliest ancestors, who looked up in curiosity and awe, to the scientists and explorers of recent times, the moon has been a faithful guide and an object of profound wonder. It drifts through the sky as the nights pass, sometimes shining brightly, sometimes hidden, but always there, watching over the earth without a sound. As we conclude this part of our journey, we take a moment to appreciate the moon's calming presence. Picture the moon rising above a still ocean, a path of light shimmering on gentle waves, and sense the quiet strength of its pull. In our fast-moving world, the moon is a constant, reminding us to pause and reflect under its pale glow. Now we prepare to leave our lunar companion and continue onward in our exploration of the cosmos. Carrying the moon's quiet lessons and enduring mysteries with us, we venture to the next chapter among the stars. In the tranquil darkness of space, another destination awaits, and the story of the universe continues to unfold, softly inviting us to listen and to wonder. Mars floats in the darkness of space as a quiet, red world. Smaller and colder than Earth, it wears a dusty red hue under a thin, pale sky. This is a desert planet of ancient rocky plains and rolling dunes. Gentle sunlight filters through a pinkish atmosphere, casting soft light and long shadows over the barren ground. The scene is calm and otherworldly, as if time itself has slowed to a hush. In this tranquil stillness, a sense of mystery lingers. For centuries, Mars was just a ruddy point of light in our sky, inspiring wonder and speculation. Now, up close, through our probes and rovers, we see a serene panorama. Vast plains, where only a faint breeze stirs the dust, and towering mountains long ago frozen in silence. Mars appears frozen in time, its silence preserving the story of a world that once might have been more alive. Unlike the bustling Earth, here there are no rustling forests or flowing rivers, only the soft whisper of wind and the occasional swirl of a dust devil. It is a tranquil solitude that speaks volumes, inviting us to listen to the quiet tales written in its rocks and sand. Mars's landscape holds a geological diary written in its rocks. One striking chapter is Olympus Mons, a volcano nearly 3 times taller than Mount Everest and the largest in the solar system. Long ago it likely poured lava down its vast slopes, but now it lies dormant and silent. Today it stands as a colossal mountain of gentle slopes, a sleeping giant watching over the horizon. On the other side of the planet stretches Valles Marineris, a canyon system that runs for thousands of kilometers. This immense canyon yawns open, its cliffs towering above a floor of broken rock. How it formed remains part of Mars's mystery, perhaps through ancient tectonic forces, or even the flow of water long ago. Now it stands empty and still, a monument to forces that have long since ceased. Mars is also covered in impact craters, each one a silent record of a meteor strike ages past. Some craters remain sharp-edged, with fresh-looking debris around them, while others have been softened by time and dust. In the far south, an enormous impact basin forms a deep bowl where thin fog or frost can collect on cold mornings. These great scars on the Martian surface recall a time of heavy bombardment, now long over. Amid these features are clues that water once shaped Mars's surface. Dry valleys twist across the terrain like riverbeds, and fan-shaped deltas mark where rivers may have emptied into lakes now gone. Orbital images even hint at ancient shorelines along the northern plains, suggesting a shallow sea might have pooled there eons ago. Over billions of years, Mars's climate changed. Its protective magnetic field faded, the atmosphere thinned, and surface water mostly disappeared into space or underground. The evidence of that transformation is carved into Mars's stone, a planet that once had running water, and perhaps a blue horizon, now quietly red and dry. Each valley and dried lakebed is a testament to those changes, preserved in the stillness of the present-day desert. The atmosphere of Mars is little more than a thin veil of gas clinging to the planet. Mostly carbon dioxide, it is less than 1% as dense as Earth's air. In this fragile envelope, you would find no oxygen to breathe and scant pressure to support liquid water on the surface. Any water exposed would boil away or freeze almost instantly. Under the daytime sky, fine dust suspended in the air gives everything a soft golden red glow. The sun, smaller and weaker than we know on Earth, shines through a hazy apricot-coloured sky at noon. Though the air is thin, it is not completely still. Winds glide over the empty plains, sometimes mustering just enough strength to lift the fine dust. On warm afternoons, little whirlwinds called dust devils dance across the landscape. They trace delicate, temporary patterns on the ground, silently stirring the red dust into the air. Occasionally, wispy clouds of ice crystals form high above, drifting lazily before dissipating in the sunlight. At dawn and dusk, these faint clouds and dust combine to paint the sky in hues of pink, orange, and even a brief soft blue at sunset. All of it happens quietly, part of a subtle daily rhythm. Mars's atmosphere may be a mere ghost of what it once was, but it still breathes in its own gentle way, shaping dunes, carrying dust, and whispering across the ages. Mars experiences seasons much like Earth, and nowhere is this more visible than at its poles. In winter, as temperatures plunge in the polar night, a white mantle of frost grows over the pole. Carbon dioxide from the thin air freezes onto the ground, forming a seasonal cap of dry ice that can stretch for hundreds of miles. The polar region becomes a silent expanse of brightness, where the sun remains below the horizon and the darkness is deep and still. In this frigid night, the surface sleeps under a blanket of frozen carbon dioxide and water ice. When spring sunlight returns, the polar ice cap sublimates, the carbon dioxide ice turns back into gas and wafts into the atmosphere. Slowly, the bright winter covering shrinks. At the North Pole, a residual cap of water ice remains even in summer, shining with a bluish-white gleam against the ruddy terrain. The South Pole, too, holds a reservoir of water ice beneath a cap of year-round dry ice. These polar caps grow and recede gently with the seasons, a heartbeat of Mars's climate. For now, the poles simply glisten in the sunlight or starlight with quiet grace, enduring the extremes of cold and light, and marking the passage of time on the desert planet. Mars is a world of dust, and sometimes that dust rises into the sky in far-reaching storms. Usually these storms are modest and local. Winds whirl over a region and lift fine reddish particles into the air, creating a haze that drifts for days. The horizon blurs, and sunlight fades to a coppery glow. But the storm eventually settles. Because the atmosphere is so thin, even a storm that covers a huge area would feel gentle if you stood in it. The grains of dust are tiny, and they hang suspended, turning the sky a deeper shade of orange, without the fierce gales we might imagine. On rarer occasions, storms can grow until they encircle the entire planet in a blanket of swirling dust. When that happens, Mars falls into a strange twilight. For weeks, the sun might appear only as a dim hint behind dusty clouds. Daylight becomes a ruddy dusk at noon, and an eerie stillness prevails. In 2018, one such global storm darkened the sky over the rover Opportunity. After nearly 15 years of exploration, the rover could no longer gather sunlight on its solar panels. In the cold darkness, it quietly drifted into an eternal sleep on the Martian plain. Thus, even the mightiest storm on Mars ends not with fury, but with a deep hush. And when the dust finally drops back to the ground, the sunlight returns, and the familiar calm of the desert planet resumes, as if Mars simply paused for a moment under a dusty veil, and then revealed its face again. Silent panoramas. Picture the silent panoramas of Mars, as if you were there. Imagine standing on a gentle rise at dawn, overlooking a shallow crater. The sunlight is just peeking over the horizon, and a soft golden glow spreads across the red-brown plain. The air is still and cold. You take a few steps. Your boots make a muffled crunch in the fine dust. Each footstep disturbs a little cloud of powder that hangs for a moment in the thin air before drifting back down. Scattered rocks and pebbles lie around you, perhaps untouched for millions of years until now. In the distance, low hills fade into a hazy pink sky. There are no sounds of life, only the faint whisper of your own movement, and maybe a gentle breeze brushing over the barren ground. As the day passes, the landscape remains quiet and vast. Rippled sand dunes catch the sunlight, their patterns slowly shifting over time under the patient push of the wind. On a far-off slope, dark streaks stain the dusty cliffs, perhaps hints that occasionally a trickle of briny water seeps down and then evaporates, leaving a fleeting mark. Evening comes, and the small sun sinks, painting the sky in pastel hues of peach and blue-grey. When night falls, Mars offers a breathtaking canopy of stars. With no thick atmosphere or city lights to interfere, the Milky Way glows brightly from horizon to horizon. Two tiny moons, Phobos and Deimos, sail through the night, looking like swift, moving stars. In this stillness, the ancient desert offers a gentle companionship. You feel connected to the cosmos in a profound, wordless way, as Mars turns slowly under your feet and the universe sparkles overhead. Over the years, we have sent robotic visitors to explore Mars, acting as our eyes and hands on the red planet. The first to arrive were the Viking landers in 1976, settling down and sending back the very first pictures from the Martian surface. They even scooped the soil to test for signs of life, an experiment that gave inconclusive results. In 1997, a small rover named Sojourner ventured a short distance from its landing site, becoming the first wheeled emissary on Mars. It examined rocks up close and showed that a robot could roam the Martian terrain. Building on that success, two larger rovers, Spirit, and Opportunity landed in 2004 in different regions of Mars. Each soon found clear evidence that water once existed in those landscapes, uncovering minerals and patterns in rocks that form only in the presence of water. These twin rovers were expected to last only 3 months, but ended up exploring for years. In time, both fell silent and came to rest, but not before greatly expanding our understanding of Mars's history. In 2012, the rover Curiosity arrived, carrying advanced instruments and a long-lived power source. It landed in Gale Crater and soon confirmed that this crater once held a lake, reading its layered rocks like pages of a history book. Curiosity found clay minerals and other clues that Mars long ago had conditions that could have supported tiny life. A decade later, in 2021, the rover Perseverance touched down in Jezero Crater, the site of an ancient river delta, to search even more directly for signs of past life. Perseverance drills into promising rocks and stores samples that a future mission might return to Earth. Along for the journey is a tiny helicopter named Ingenuity, which proved that powered flight is possible in Mars's thin air by hopping above the desert floor. High above, orbiters map the planet and relay data, acting as silent sentinels for the rovers. From the Vikings to Perseverance, each mission has added to our understanding of Mars, bringing this distant world closer and paving the way for the day when humans will finally stand on this quiet planet. One of the most profound questions our exploration seeks to answer is whether Mars ever supported life. That question is tied to water, since all known life depends on liquid water. Mars today is dry, but in the distant past it had rivers, lakes, and perhaps even seas. Most of that water is gone now, lost to space or locked in ice beneath the ground. Still, traces remain. Plenty of water is frozen in the polar caps and buried under the soil. Occasionally, Mars offers a tease that a little liquid water may still flow. Dark streaks appear on some warm slopes, hinting that briny water might seep down briefly before evaporating into the thin air. Because Mars once had water, the search for past life focuses on places that were wet long ago. If life ever took hold on Mars, it likely lived as tiny microbes in those ancient lakes or springs. Our rovers drill into clay-rich rocks formed in water, looking for organic molecules or other possible traces of biology. Curiosity has detected organic compounds in Martian rock, basic building blocks of life. Traces of methane gas have also been found in Mars's thin air. On Earth, methane often comes from living microbes, so its presence on Mars is an intriguing mystery. So far, however, no clear sign of life, past or present, has been discovered. Mars keeps its secrets well. Every clue is subtle, and each answer seems to lead to new questions. Still, the search continues quietly and steadily. Each rock analysed is a gentle question posed to Mars. Did life ever live here? The planet has not answered yet, but we listen with patience. Perhaps one day, with more samples or even human explorers digging into its soil, we will uncover evidence that reveals the truth. Until then, the mystery remains, inviting us to stay curious and hopeful, yet calm and patient as we await whatever stories Mars has yet to tell. We quietly anticipate the day when humans will walk on this red desert world. People have long dreamed of visiting Mars, and soon those dreams may become reality. In the not-too-distant future, A spacecraft could descend to the Martian surface, carrying a crew of explorers. Imagine that moment. The lander's engines shut off, dust settles, and silence returns. Then a new sound. The soft crunch of a boot on alien soil signals that humans have arrived. The first astronaut steps onto Mars, leaving a footprint in the rust-colored dust. Above, the sun shines in a pale sky, and Earth glimmers as a tiny blue star. In that quiet, historic moment, we will become part of Mars, no longer just observers from afar. Their initial stay will likely be brief and careful. The astronauts will set up a small camp and spend days or weeks exploring around their landing site. They move slowly and deliberately, knowing that Mars rewards patience. Each evening, they might pause to watch the sun set over the barren landscape, feeling both the distance from home and a deep connection to this world. Even a short visit will leave its mark. Human voices will be heard where before there was only wind, and footprints will press into ground that waited ages for their arrival. Mars waits patiently, as it has for eons, untouched by human hands. When we finally set foot on Mars, it won't be a conquest. It will be a respectful visit. We will bring our curiosity and care, hoping to learn while disturbing the quiet as little as possible. One day, a group of people will stand and gaze at the Martian horizon, feeling the ancient stillness of the planet around them. In that tranquil moment, they become part of a new chapter of Mars's story. A humble beginning for humanity, made gently and in harmony with the timeless silence of this world. Mars, the silent desert planet, has shared its story with us in gentle whispers. We have witnessed its ancient volcanoes and dry riverbeds, its pink skies and polar frost, its dusty storms and quiet nights of stars. Through our imagination and our mechanical envoys, we have walked its plains and listened to its winds. The red world's calm solitude has given us perspective and peace, a reminder of the quiet resilience of a planet that has endured for ages. We leave Mars with respect and a sense of tranquility, carrying with us the subtle lessons it taught about patience, change, and wonder. Our journey through the cosmos will continue. Beyond Mars, other worlds await, each with its own stories and mysteries. For now, we take a moment to breathe and appreciate the stillness we have experienced. As we prepare to venture onward to the next destination, we do so softly, keeping the gentle spirit of Mars in our hearts. In this peaceful pause, we linger under the imagined Martian sky a little longer, then calmly set our sights on the path ahead, ready to continue the voyage when the time comes. Far beyond the familiar planets that circle our sun, countless unseen worlds quietly orbit distant stars. In the silent darkness between the stars, these exoplanets, planets outside our solar system, have long been the subject of human wonder. For generations, people gazed at the night sky and softly imagined, could there be other worlds out there circling those pinpoints of light? In recent decades, we have finally begun to discover these distant planets, confirming that the cosmos holds far more worlds than we ever knew. The discovery of exoplanets has opened a new, tranquil frontier of exploration, one that unfolds not with sudden drama, but with patient observation and quiet revelation. In this calm cosmic ocean, stars are like islands, each with the potential to host its own family of planets. Yet these planets are invisible to our eyes, hidden in the brilliance of their parent star's glow. To find them, astronomers learn to detect the faintest whispers in starlight and the subtlest gravitational tugs. The search for exoplanets is a story of subtlety and perseverance, a slow, careful reading of the heavens that requires immense precision and patience. It is a pursuit that matches the stillness of space itself, where changes unfold in gentle rhythms and soft cycles. The first hints of exoplanets were tiny clues embedded in the light of distant stars. Imagine a star shining steadily in the darkness. If a planet orbits that star, its gravity pulls on the star ever so slightly, causing the star to wobble in place. From our far vantage, we cannot see the planet itself, but we can detect the star's gentle wobble by observing its light. As the star moves toward and away from us, its light shifts subtly in color, like a delicate change in tone. By using sensitive spectrographs to measure these shifts, scientists can infer the presence of an orbiting planet. This technique, known as the radial velocity method, was how astronomers confirmed the first planets around sun-like stars. It was as if the star was quietly telling us of its hidden companion through a slight, regular change in its light. About 30 years ago, using this patient, listening to starlight, researchers confirmed a landmark discovery: a planet circling another sun. To their surprise, it was a giant planet in a scorchingly close orbit, completing a full circuit in just a few days. No one had expected a Jupiter-sized world to be so near its star. This quiet revelation marked the dawn of a new era. For the first time, we knew for certain that other suns do have planets, and some turned out to be very different from those in our own solar system. Before long, more stars were observed to wobble with that subtle regularity, each signal hinting at an orbiting world. Over time, astronomers refined their ability to detect these slight stellar wobbles with greater accuracy. Large telescopes with ultra-precise instruments focused on one star after another, night after night, gathering light and splitting it into spectra to watch for tiny shifts. The process was slow and meticulous. After weeks and months of observations, patterns emerged from what initially looked like random noise. One star's spectrum might shift back and forth every few days, indicating a planet whipping around in a tight, fast orbit. Another star might show a much slower oscillation, perhaps over many months, suggesting a more distant planet. Each wobble, no matter how slight, became a clue to an unseen world's presence and its orbital period. Listening for a star's wobble is akin to hearing a faint musical note in an otherwise silent room. It requires a gentle touch and a trained ear. Through this method, many planets were gradually uncovered. Some huge gas giants skimming close to their stars, others farther out tugging more subtly. The radial velocity technique remains a fundamental way we find exoplanets. There is quiet beauty in discovering something so significant through such a slight effect. It reminds us that in the vast hush of space, even a small planet can make a star sing a soft gravitational song that we can detect across light years. Around the same time, another subtle method was developed to find elusive worlds. Instead of listening for wobbles, astronomers began watching for delicate shadows. If a planet's orbit is aligned just right, it will pass directly between its star and our viewpoint, briefly blocking a small portion of the star's light. When this happens, the star dims ever so slightly for a short while. Imagine a tiny moth drifting across the face of a distant lamp. For an instant, the lamp's light flickers almost imperceptibly. This event is called a transit. By carefully measuring a star's brightness over time, scientists can catch these minute dips in light and deduce that a planet is crossing the star's face. The transit method also demands extraordinary precision and patience. Most stars shine with nearly constant brightness, so any dip from a transiting planet is extremely small. But with sensitive instruments, those tiny eclipses become evident in the data. A star's light might drop by only a few hundredths of a percent during a transit, far too subtle for our eyes to notice. Yet precise detectors can discern it. If the same slight dimming repeats at regular intervals, say every 10 or 50 days, it reveals a planet with that orbital period. From these transits, astronomers can estimate a planet's size and even glean hints about its composition. The discovery of planets via transits opened a new window onto the richness of distant worlds, allowing us not only to find planets, but also to begin measuring their properties. Detecting these patterns requires patience, but the reward is the gentle confirmation that a new world is indeed there. To truly embrace this patient approach, astronomers launched special space telescopes dedicated to watching stars for these subtle signals. One of the most successful was the Kepler Space Telescope. For almost a decade, Kepler gazed steadily at one small patch of sky, monitoring the brightness of over 150,000 distant stars without interruption. In the silent vacuum of space, Kepler kept its electronic eye fixed, looking for the faint telltale dips of transiting planets. It was an extraordinarily focused and quiet vigil. Over the years, Kepler's calm persistence was richly rewarded. From a gentle stream of starlight data, the presence of thousands of new planets gradually emerged. Kepler detected planet after planet by catching their delicate shadows, discovering worlds ranging from massive Jupiter-like giants to others smaller than Earth. By the end of its mission, Kepler revealed that planets are incredibly common. Perhaps most stars have at least one. This profound insight arrived not through a single dramatic finding, but through many small, steady observations, building up over time. It taught us that with patience and precision, the universe will unveil its secrets, showing that the twinkling stars overhead are often accompanied by their own quiet worlds. Following Kepler's legacy, a newer mission called TESS, Transiting Exoplanet Survey Satellite, continues the search on a broader scale. TESS surveys large swaths of the sky, focusing on nearer, brighter stars. Night after night, TESS monitors thousands of stars, looking for the same gentle dips in brightness that signal a planet's transit. Because it targets closer stars, the planets TESS finds are generally nearer to us and easier to study further. With a methodical, unhurried approach, TESS is steadily adding more discoveries to the catalogue of distant worlds. Together, these space telescopes act as silent observers of the heavens. They watch and wait, catching faint whispers of new planets in the starlight, and sending the data back to Earth for us to decipher. It's a quiet collaboration between human curiosity and nature's subtle signals, yielding profound discoveries without fanfare. As our methods uncovered more exoplanets, a stunning diversity of worlds came into view. Each discovery added new colours to the cosmic canvas of planetary systems, revealing far more variety than we see in our own solar neighbourhood. Some of the first planets we found were enormous gas giants orbiting scorchingly close to their stars, the so-called hot Jupiters. Imagine a Jupiter-like planet so near its sun that it races around in just a few days, its atmosphere heated to extremes and perhaps gently puffing away under the intense starlight. In contrast, other planets emerged at the opposite extreme, giant worlds circling far from their stars, in deep cold and darkness. These distant giants receive only a weak glimmer of light and move slowly, taking decades or centuries to complete a single orbit. Discoveries at these two extremes showed us that planets can exist in environments we once thought unlikely. Between those extremes lies a rich menagerie of intermediate worlds. Many stars have super-Earths, planets a bit larger than Earth but smaller than Neptune. We have no such planet in our own system, which made their discovery a surprise. Some super-Earths might be predominantly rocky, bearing thick atmospheres or vast highlands. Others could be more like scaled-down gas planets, wrapped in hazy layers of cloud. Often these worlds orbit at moderate distances, not too hot and not too cold. We can imagine some with gentle climates or even global oceans, though much about them remains a mystery. The existence of super-Earths has expanded our understanding of what a planet can be, introducing types of worlds we had never seen before. Even more intriguing, astronomers have found planets akin to our Earth, orbiting in the comfortable warmth of their stars' habitable zones. The habitable zone is the region where conditions might allow liquid water on a planet's surface, a key ingredient for life as we know it. In one remarkable system, a tiny dim star was found to host 7 Earth-sized planets, several in that star's habitable zone. We can hardly imagine what those worlds are truly like. Perhaps some are rocky globes shrouded in clouds beneath a cool red sun. But their existence is profoundly hopeful, suggesting that Earth-like planets are indeed out there. Planets have also been found in places that once seemed unlikely. We now know of planets orbiting double stars, places where, if you stood on one of those worlds, you would see 2 suns moving across the sky. There are planets so light and puffy in composition that they are almost like balls of cotton, and others so dense and heavy they might be mostly iron. Some planets likely have molten landscapes of lava, while others could be covered in deep global oceans. Astronomers have even found lonely planets drifting through space with no star to orbit. This astonishing variety shows how diverse and resilient planet formation can be. Yet despite their differences, each of these distant worlds follows a quiet path around its sun, a serene participant in the cosmic dance. One of the most calming realizations about these distant worlds is that they all move to steady cosmic rhythms. Every exoplanet is a traveler on a repeating journey around its star, moving with a certain dependable tempo. When a planet transits its star every 10 days, for example, we observe a gentle dip in the star's light every 10 days, like a soft metronome tick marking the passage of time. There is something deeply soothing in knowing that, far beyond our reach, a planet is circling in a stable, predictable way, kept on course by the quiet pull of gravity. Consider one such distant world. It orbits a sun-like star about 500 light-years away and takes roughly 100 days to complete one orbit. For billions of years, it has traced that same path around its star. Eons before we knew to look, and likely eons after, like a slow, unending waltz. Every time it passes in front of its sun, the star's light, as seen from Earth, dims just slightly. In the stillness of that event, a few photons of the star's light fail to reach us, blocked by the planet's silhouette. Those missing photons are a whisper from that far-off system, announcing, "I am here." When our instruments pick up that faint whisper, it links us momentarily to that distant planet. Yet the planet itself remains utterly unaware of our attention. It continues along its orbit, oblivious to the fact that on a blue world across the galaxy, we have noticed its presence and found wonder in it. Each planetary system has its own quiet symphony of motion. It's comforting to think that across the galaxy, countless planets are endlessly orbiting, each following a steady beat. Like dancers in a cosmic ballet, some even move in near-perfect harmony with their neighbors. But even alone, Every planet contributes to this silent music of the cosmos. This gentle order in the heavens provides a reassuring backdrop to the universe's vast expanse. Knowing that the galaxy is teeming with exoplanets changes the way we see the night sky. When we look up, we no longer see just lonely, distant stars. We sense that each star could be a sun with its own family of worlds. The Milky Way above becomes more than a river of light. It is a vast collection of cosmic neighborhoods, each with its own planets drifting in the great quiet. This realization invites a peaceful kind of contemplation. On a clear night, under the hush of stars, we might feel a gentle connection to those far-off worlds. They are no longer mere points of light or abstract data, but real places out there in the cosmic ocean. We have confirmed thousands of exoplanets so far, and there are likely billions more in our galaxy waiting to be discovered. This abundance of worlds expands our perspective and stirs the imagination. We quietly wonder how many might be like Earth with familiar blue skies and water, and how many utterly alien. Could some of these distant planets harbor life? Perhaps somewhere on a faraway world under an alien sun, living beings look up and marvel at their sky as we do at ours. We have no answers yet, but just knowing these other worlds exist makes the universe feel richer and more inviting. It reminds us that Earth, while precious, is not the only world. It is one among many, and that knowledge brings both awe and humility. Each new exoplanet discovery is a small triumph of patience and ingenuity. Without ever leaving our planet, we learn to detect these distant worlds by carefully watching starlight for subtle changes. This gentle pursuit of knowledge is a testament to human curiosity and dedication. Our journey through space is far from over. The worlds we have found so far are just the beginning of what lies beyond. In the soft darkness of the cosmos, countless more planets quietly circle their suns, waiting for us to notice their subtle signals. For now, we can let the enormity of a galaxy filled with worlds wash over us. It is a peaceful thought, a cosmos rich with other planets, each a silent story unfolding in the night. As we gently conclude this chapter of our exploration, we carry forward a sense of calm wonder. There is much more to discover, and we will continue our cosmic journey with the same slow, steady curiosity, ready to explore further whenever we feel the call of the stars. Space exploration is a symphony of subtle technologies working in concert. In the darkness beyond our world, every movement of a spacecraft, every signal sent across the void, and every breath taken by an astronaut is supported by quiet engineering marvels. In this gentle chapter of our journey, we explore the patient, measured technologies that make exploration possible. From the steady roar of launch fading into silent orbit, to the soft whir of life support fans and the faint whisper of signals across space, these systems guide our spacecraft with calm precision and endless persistence. Let us drift through each of these technologies, appreciating how they quietly enable humanity's voyage among the stars. Every journey to the stars begins with the graceful force of a launch. A rocket sits poised on the pad, tall and silent against the sky. Inside its metallic body, fuel and oxidizer are kept chilled and still, awaiting the moment of ignition. The countdown unfolds slowly in a measured cadence, each number an invitation to focus and prepare. When the engines ignite, bright flames blossom beneath the rocket, and for a heartbeat the scene can seem almost silent from afar. The rocket rises slowly at first, shaking off the bonds of gravity with a controlled, powerful grace. Even though launching a spacecraft is a feat of immense power, it is guided by gentle precision. Computers throttle the engines delicately to balance the rocket, keeping its ascent smooth and aligned. As it soars upward, it passes through clouds and thin air, the thunder of launch gradually diminishing behind it. Stage by stage, parts of the rocket complete their duty and fall away, a quiet shedding of weight that allows the journey to continue ever higher. Each staging is a brief separation, choreographed to minimize jarring motions, so the delicate payload experiences as little stress as possible. The result is a serene, planned ride to orbit, a careful ballet of machinery lifting explorers beyond the sky. High above the Earth, the final engine shuts down and the launch vehicle releases its spacecraft. In that moment, the once deafening roar has given way to the profound silence of space. The payload coasts free, as weightless as a drifting feather. What began with controlled fire and thunder now transitions to quiet gliding. The launch system's role is complete. It has gently placed the spacecraft on the threshold of the cosmos. With the Earth's atmosphere behind it, our craft is now ready to rely on other technologies to continue its journey among the stars. After reaching the calm of space, a spacecraft must still be guided to its destination. Propulsion systems provide the means to journey onward, and they do so with patient persistence. Different propulsion methods work in unique ways, each with its own gentle character. Some give a quick push to adjust a path, while others provide a continuous, subtle nudge over long periods. All are designed to operate in the near vacuum of space with reliability and grace, steering spacecraft through the vastness. Common spacecraft propulsion methods. Chemical thrusters. These are the traditional rocket engines that burn fuel and expel hot gas for thrust. In space, chemical thrusters fire in brief, controlled bursts. A short puff might adjust a satellite's orientation or nudge a spacecraft onto the correct course. Unlike the dramatic launch engines, these smaller thrusters operate with a restrained power. Each firing is calculated and brief, imparting just enough change. The result is a gentle course correction or a slow orbital insertion, carefully planned by engineers and executed in silence except for the faint click of a valve and the push of gas into vacuum. Ion propulsion. An ion thruster provides one of the most serene forms of propulsion. Instead of combusting fuel explosively, it uses electricity, often from solar panels, to charge and accelerate ions, electrically charged atoms, out of the engine. Each ion departs at extremely high speed, imparting a tiny push to the spacecraft. The thrust is almost imperceptible in any single moment, comparable to the weight of a few falling feathers, but it is continuous. Over weeks and months, these ions streaming out relentlessly accelerate the spacecraft to great speeds. The glow of an ion thruster is often a soft electric blue, and its operation is so quiet and steady that it resembles a gentle cosmic breeze pushing the craft forward. Space probes like Dawn have used ion engines to calmly spiral from one asteroid to another, the patient thrust guiding them across millions of kilometers with perfect poise. Solar sails. In the most silently poetic form of propulsion, solar sails harness the light of the sun itself. Sunlight carries momentum, and a broad mirror-like sail can catch those light particles, photons, much like a sailboat catching the wind. The push from sunlight is extremely gentle, far lighter than the touch of a hand, yet in the frictionless void of space, even this faint pressure can slowly move a spacecraft. A solar sail unfolds like a delicate silver flower, opening to the sunlight. With every moment, countless photons bounce off the sail's surface, each one imparting a minute push. Over time, these pushes add up. The spacecraft gradually builds speed, gliding through space propelled by sunlight alone in an elegant and soundless journey. There are no moving parts, no fuel consumed, just a quiet ride on sunbeams, demonstrating how patience and ingenuity can turn even light into a means of travel. All these propulsion methods work together or in sequence to guide spacecraft. A mission might begin with chemical engines for quick maneuvers, then switch to ion propulsion for an extended cruise. At times, gravity itself becomes a propulsion assist. By flying past planets in carefully planned paths, spacecraft can borrow a bit of the planet's motion. These gravity assist maneuvers are another calm marvel. No engines required, just a silent gravitational tug that flings the spacecraft onto a new trajectory. In each case, whether using fuel, electricity, or sunlight, propulsion systems operate with a balance of force and finesse. They ensure that after the dramatic leap to orbit, our exploration continues across the solar system in a slow, steady voyage. When humans travel into space, they bring a small bubble of Earth's environment with them. Life support systems are the caretakers of that tiny, fragile bubble, working continuously and quietly so astronauts can live and breathe far from home. Inside a spacecraft or space station, you wouldn't hear the harsh sounds of machinery. Instead, you might notice a soft hum of ventilation fans and the gentle whoosh of air circulation. These sounds become the background lullaby of life in orbit, as routine and reassuring as crickets on a summer night. The technology operates in steady rhythms to provide all the necessities of life in a place where none naturally exist. Life support systems quietly handle breathable air. A mixture of oxygen and nitrogen is carefully maintained at the right pressure. Scrubbers draw in exhaled air and remove carbon dioxide, often using chemical filters or materials that absorb CO2. In some systems, the trapped carbon dioxide is even recycled, converted back into oxygen through reactions or by feeding it to plants in experimental space gardens. Fresh oxygen can be generated by splitting water molecules using electrolysis, a process that produces oxygen for the crew and hydrogen as a byproduct. All of this happens behind the scenes. To the astronauts, it feels no different than breathing on Earth. The air remains clear, odorless, and refreshing. Only the knowledge that a complex system is constantly purifying and refreshing the atmosphere reminds them that every breath is a gift of technology. Water recovery and purification. In the closed environment of a spacecraft, water is precious. Every drop of water is conserved and reclaimed through purification systems. Humidity condensing from the air, the water in an astronaut's exhalation and sweat, and even urine are captured and filtered. Advanced filters and chemical processes remove impurities and make the water clean and safe to drink again and again. The water tastes just like pure water on Earth. Astronauts often say you wouldn't know it was recycled at all. The recycling process is quiet and unassuming, tucked away in equipment racks. It works steadily, turning yesterday's coffee into tomorrow's tea, ensuring the crew has enough water for drinking, preparing food, and hygiene. Knowing that this system is running gives a profound sense of interconnectedness. Every use of water feeds back into the cycle, much like on our home planet's ecosystem, but accelerated and contained within a spacecraft. Temperature and climate control. Space is an environment of extremes, with sunlight that can overheat and shadow that can freeze. Inside, however, the climate is kept comfortably Earth-like. Thermal control systems circulate fluids that carry heat away from electronics and people, radiating excess warmth into space through radiator panels that release heat as faint infrared rays. Heaters ensure that in the cold of orbital darkness, temperatures don't drop too low. The result is a steady, mild temperature, around room temperature, where astronauts can work in shirt sleeves. The ventilation system gently moves air around, preventing any hot or cold spots and giving the sensation of a light breeze. This consistent climate is maintained without fanfare. The crew might only notice a slight airflow or the gentle click of a thermostat kicking in. It's a cocoon of warmth in the cold void, all managed by systems that react in real time to keep everything just right. Food and waste management. Even eating and cleanliness have technological support. Compact ovens or warmers allow crew to heat their meals, and special hydration stations mix water with dehydrated foods to make them palatable. After meals, packaging and waste are carefully stored and processed to avoid any contamination of the living space. There are systems to handle waste discreetly, often by compressing and storing it for disposal when a cargo craft departs. Nothing is left to chance. Even crumbs and bits of debris are captured by filters so they don't float around. The entire process of living, eating, drinking, breathing, and cleaning is facilitated by life support technology operating quietly in the background. This allows astronauts to focus on their work and the view outside, almost forgetting that the harsh vacuum lurks just beyond the walls. Together, these life support components create a stable haven amid an inhospitable environment. They work continuously and often redundantly, with backups ready, to ensure there is never a pause in their protection. The elegance of a life support system is in how routine it makes the essentials of life. An astronaut wakes, breathes, eats breakfast, and prepares for the day's tasks in space with the same ease as if they were at home. The machinery fades into the background, offering comfort and safety. In this gentle reliability, life support systems give astronauts the freedom to live and explore space day by day with the assurance that their essential needs are quietly being met. Not all explorers in space are human. In fact, many of our greatest journeys have been undertaken by robots, mechanical companions that travel alongside us or venture where humans cannot yet go. These robotic explorers range from planetary rovers to orbiting probes to the robotic arms that assist astronauts in space. Though made of metal and circuits, they move with surprising delicacy and intent, guided by our commands and their own programmed intelligence. In the stillness of space or on the surface of distant worlds, robots carry out their tasks with patient determination, extending our reach with their durable presence. Imagine a rover on Mars, greeting the soft light of dawn on the red planet. It sits quietly through the cold Martian night, powered down to conserve energy. As the sun rises over the rust-colored horizon, the rover's solar panels soak in the light, and it gently reawakens. There is no rush in its movements. Every action is slow and careful, by design. The rover slowly turns its camera head to survey the surroundings, taking in the landscape as a solitary visitor. When it receives instructions from Earth, perhaps to investigate a nearby rock, it begins to roll forward at a pace of only a few centimeters per second. The wheels crunch softly on the soil, a sound that would be barely audible even if you stood next to it. This unhurried pace is intentional, ensuring the rover remains stable on uneven ground and giving it time to detect obstacles. Over hours, it traverses distances we would consider a short walk, pausing occasionally to observe, or to let its computers calculate the safest path. Such patient roving has allowed machines like Spirit, Opportunity, and Curiosity to explore for years beyond their expected lifetimes, quietly rewriting our understanding of Mars, one rock at a time. In orbit around Earth, robotic helpers are equally graceful. The International Space Station is equipped with a robotic arm, often called Canadarm2, which is a marvel of smooth control. When a supply spacecraft approaches the station, Canadarm2 reaches out slowly, as an angler might gently dip a net into water. Inch by inch, the long arm extends, its joints moving with measured precision. There is no sudden motion as it closes in on the visiting spacecraft's handle point. Instead, it glides to a stop and latches on with steady assurance. The astronauts inside watch on screens as their mechanical teammate captures the supply ship, and they often comment on how mesmerizing the slow ballet of the robotic arm is. It moves so steadily that it can appear almost alive, yet it only follows commands given from the crew or even pre-programmed sequences. Once attached, the arm carefully guides the incoming vessel to dock with the station. All of this happens in silence, the only sounds being the faint vibrations through the station structure as motors turn somewhere outside. This delicate dance of machinery brings fresh supplies and experiments, a routine yet amazing occurrence made possible by robotics. Farther out in space, we have probes like Voyager, Cassini, or New Horizons, which acted as our eyes and ears in places we've never been. These spacecraft are essentially robots too, carrying instruments and cameras to observe distant planets and moons. They operate largely on their own, with preset instructions because the distances are too great for real-time control. When Cassini orbited Saturn, it was essentially an autonomous robotic explorer living in the ringed planet's domain. Each time it swung by a moon like Titan or Enceladus, it pointed its instruments, took photographs, sniffed the environment with its sensors, all according to a carefully crafted but autonomously executed plan. From millions or even billions of kilometers away, we could only listen as the probe faithfully performed its duties in the quiet of space. These robots have to endure harsh radiation, extreme temperatures, and long periods of darkness. Yet they persist with a steady resilience, continuing their tasks until one day their power runs low or their mission ends. Their legacy is vast troves of data and images sent back to Earth, transmitted through the void by their communications systems. Robotic explorers, whether rovers, arms, or probes, embody the union of human ingenuity and machine endurance. They allow us to touch other worlds and environments gently, with sensors instead of fingers and wheels instead of feet. Each robot is built to be as self-sufficient as possible, performing complex tasks with minimal input. In their patient, methodical way of working, they teach us the value of steady progress. There are no hasty movements or reckless dashes. Everything is measured and deliberate. And so, in the grand journey of exploration, these mechanical companions move alongside us, quietly accomplishing feats that would be impossible for fragile humans, and extending our presence to worlds we can only dream of visiting ourselves. In the silent expanse of space, power is the lifeblood that keeps all systems running. Most spacecraft turn to the sun as their primary source of energy, capturing its gentle rays with wide, sensitive wings of solar panels. Solar power in space is a study in quiet efficiency. With no atmosphere to dim the sunlight, these panels can generate electricity whenever they face the sun, and they do so without any moving parts or noise. The process is elegant. Photons of light strike the solar cells, exciting electrons and creating a flow of electricity. It all happens silently, on a microscopic level, yet scaled across an array the size of a room or a football field. It produces ample power for a spacecraft's needs. When a satellite or station first reaches orbit, deploying the solar panels is a crucial and delicate moment. Often, the panels are folded tightly during launch, like the folded wings of a resting butterfly. Once in the weightlessness of space, small motors or springs slowly unfurl them. An astronaut watching from nearby would see the solar panels extend outwards almost magically, unfolding segment by segment in a slow, steady motion. There might be a soft whir or click as latches lock them in place, but mostly it is a visual spectacle conducted in silence. As the panels spread open, they reveal their glossy, dark surface to the sun. Almost immediately, electricity begins to flow. On the International Space Station, for example, the large golden arrays unfurl to their full span and then gently begin rotating to track the sun. This rotation is leisurely, imperceptibly slow to a casual glance, yet constant, ensuring the panels face the sunlight directly. The station's power system stores excess energy in batteries during the 45 minutes of daylight in each orbit, then provides that energy during the 45 minutes of eclipse when the station is in Earth's shadow. All of it happens seamlessly, the station glowing with electricity even as it passes into night, thanks to the quiet work of solar cells and batteries. Deep space probes rely on solar power too, though when venturing far from the sun, the sunlight grows weak. These spacecraft carry impressively large solar wings to gather every bit of light, like a thirsty plant spreading wide leaves. For instance, the Juno spacecraft orbiting Jupiter has enormous solar panels that allow it to operate over 700 million kilometers from the sun. Juno's 3 panels extend outwards, each as long as a semi-trailer truck, soaking up what little sunlight reaches that far. Despite the faintness, those panels quietly convert light to power, enabling Juno's instruments to run and send us discoveries from Jupiter's realm. The entire process is steady and uncomplaining. The sun shines, the panels receive, an electric current flows. In some cases where the sun's light is too dim, like missions to Saturn and beyond, spacecraft turn to a different, equally steady power source, radioisotope generators. These devices use the heat from the natural decay of radioactive materials, like a small pellet of plutonium, to generate electricity. They are essentially electric generators with no moving parts, providing a continuous trickle of power, day and night. The Voyager probes, still communicating after nearly half a century, use this method. It is a quiet heat source that gradually diminishes over decades, akin to a slowly cooling ember. Whether through sunlight or a steady nuclear battery, the power systems of spacecraft are designed for reliability. They provide energy gently and consistently, enabling all other systems to function. One might think of them as the beating heart of a spacecraft, though their beat is a silent flow of electrons. With their power assured, spacecraft can carry out ambitious missions, confident in the sun's rays or a tiny nuclear warmth to keep them alive in the cold of space. As our robotic explorers travel through the cosmos, they must observe and interact with their surroundings. This is the role of sensors and scientific instruments, the eyes, ears, and inquisitive senses of a spacecraft. These devices quietly gather information, often in ways that extend beyond human senses, capturing images and data about distant worlds and cosmic phenomena. Designed with exquisite sensitivity, they operate with precision, usually without making a sound. But their impact is profound. They convert the silent realities of space into signals and pictures we can understand back on Earth. One of the most familiar sensor systems on spacecraft is the camera. Far from a simple snapshot device, a space camera is a highly refined instrument. It might be designed to take panoramic images of a planet's surface, or to zoom in on a distant moon, or to capture faint starlight. Consider the cameras on the Hubble Space Telescope, which have collected light from galaxies billions of light years away. Hubble's sensors open their electronic eyes and gather photons that have been traveling for eons. The process is silent and invisible, but if one could imagine it, it's like holding out a hand in the dark and feeling the soft patter of ancient rain, except the rain, here, is light particles from the deep universe. Over long exposures, Hubble's instruments accumulate these particles to form an image, revealing stunning vistas of nebulae and star clusters. Each exposure can last minutes to hours, a patient gaze at the heavens, and at the end, an image emerges where before there was darkness. All of this occurs with no noise or fuss, just the steady integration of light guided by finely tuned sensors. On planetary probes, sensors take many forms beyond visible cameras. There are spectrometers that break down light into its colors to identify the fingerprints of minerals and gases, a way of smelling or tasting a planet's composition using light. A spectrometer might observe the sunlight reflecting off a moon's surface or passing through a planet's atmosphere and quietly record the signature of water, or methane, or other elements in the light. Magnetometers are like compasses that can sense magnetic fields. A spacecraft carrying one can map the invisible magnetosphere of a planet, such as Jupiter, tracing its intensity and shape. This too is a silent measurement. The magnetometer's readings change as the craft flies, and those numbers tell a story of swirling charged particles and planetary cores. There are also radiation detectors clicking away imperceptibly, counting cosmic rays or solar particles, and seismometers that might sit on a moon or asteroid, feeling for faint tremors or impacts. Each instrument operates methodically, often slowly accumulating data over time. The beauty of these sensors is how they work together to give a complete picture. For example, during its gentle orbit of Saturn, the Cassini spacecraft carried a suite of instruments. As it flew by the moon, Enceladus, its cameras took pictures of geysers of ice erupting from the surface, while its spectrometers analyzed the composition of those icy plumes, and its dust detectors actually caught and measured tiny particles from them. In that moment, Cassini was like a curious traveler using all senses at once, seeing the jets, feeling the particles, and tasting their chemistry, all in the span of a silent flyby. The spacecraft then turned those sensory experiences into data signals and sent them across space to Earth. For us listening, or reading comfortably, it's calming to know that these explorations are happening gently, millions of kilometers away, without disturbance. There's a rover on Mars, quietly scanning a rock with a laser spectrometer. The ping of the laser too high-pitched to hear, and the only hint of its work, a small puff of dust. There's a probe around a distant comet, sniffing the faint gases released as it warms in sunlight. Each sensor is a channel of curiosity, operating steadily. Through them, a silent universe speaks in numbers and images, and our spacecraft dutifully listen. The data will travel back to Earth, where scientists and engineers eagerly await the next transmission, ready to interpret the secrets these patient instruments have uncovered. Space is vast, and many of our spacecraft travel so far from Earth that they must rely on themselves to handle day-to-day operations. Autonomous systems are the internal brains and nerves of a spacecraft, enabling it to make decisions or adjustments on its own when needed. This autonomy is a quiet form of intelligence, software and circuits humming along, keeping the craft safe and on course without direct human control. In the emptiness of space, this self-reliance is essential. Communication with Earth can take minutes or hours, and there are times when no one is listening at all. For instance, when a spacecraft slips behind a planet and is temporarily out of radio contact. At those moments, the spacecraft's ability to handle things calmly on its own becomes vital. One of the primary tasks of an autonomous system is attitude control, maintaining the spacecraft's orientation. To keep solar panels facing the sun or antennas pointed toward Earth, the spacecraft uses internal devices like reaction wheels and gyroscopes. Reaction wheels are like spinning tops. By speeding them up or slowing them down, the spacecraft can turn itself with precision. This happens gradually and without any external thruster firing. If you were aboard a spacecraft adjusting its attitude with reaction wheels, you might hear a faint whir as a wheel spins up and feel a gentle, almost unnoticeable shift as the vehicle begins to rotate. These adjustments allow the craft to align itself for the next task, perhaps pointing a camera at a target or angling a thruster for a course correction. All of it is handled by the guidance computer following preset rules. If the craft is off by a degree, correct it slowly in the opposite direction. If a wheel is reaching its limit, use a small puff from a thruster to unload the excess momentum. This constant balancing act keeps the spacecraft stable and oriented, like a seafaring ship automatically adjusting its sails to stay on course amid shifting winds. Spacecraft autonomy also involves managing power and systems health. The onboard computer gently monitors battery levels, temperatures, fuel reserves, and the status of all instruments. If power is running low, the computer might decide to shut down a non-essential instrument for a while to conserve energy. If an instrument is overheating, it can turn on cooling systems or orient the spacecraft differently to shed heat. These decisions are made using a hierarchy of logic that engineers on Earth have carefully programmed. In many ways, engineers imbue the craft with a bit of foresight. If X happens, respond with Y. The spacecraft carries these instructions like a handbook. It can consult in a split second when needed. Most of the time, nothing dramatic happens. It simply cruises along, all systems normal, with the computer checking and rechecking that all readings are within expected ranges. It's a bit like a vigilant caretaker that paces the halls of a quiet house at night, making sure every door is secure and every appliance is functioning smoothly. Perhaps the most critical moments for autonomous systems come during deep space maneuvers or encounters. When the New Horizons probe flew past Pluto, there was no way for it to be joystick controlled from Earth in real time. It was moving too fast and far. Instead, New Horizons had an onboard sequence of commands and the autonomy to carry them out, taking photos, rotating to scan the surface, collecting particle data, all in a tight window of hours as it sped by the dwarf planet. If something unexpected occurred, the probe had fault protection routines, a kind of self-preservation script. For example, if it sensed that a guiding star was lost from view or a gyro was acting up, it could automatically switch to a backup system or go into a safe standby mode and wait for further instructions. This ability to enter safe mode is common. The spacecraft essentially says, "Something isn't right. I will just keep my vital systems on and wait quietly for help." And indeed, many times spacecraft have gone to safe mode and patiently called home for help, transmitting a simple beacon signal that engineers detect. Once the problem is resolved, via new commands from Earth, the spacecraft obediently returns to its normal duties. In the context of our gentle journey, autonomous systems are the unsung heroes working silently within every probe and rover. We don't often hear about them, because when they work well, nothing seems to happen at all. Everything just functions. There is comfort in that for mission teams and for us as explorers, knowing that millions of miles away, our spacecraft can take care of themselves, even if just for a little while. It means that exploration does not have to pause when Earth is asleep or busy. The probe will keep watching, measuring, and steering itself through the void. This quiet intelligence aboard each craft ensures that our reach can extend far and our presence can be maintained even when we're not actively intervening. It's as if we've sent a trusted envoy that we know will behave wisely on its own as it travels through the unknown. Every spacecraft exploring beyond Earth wants to tell us its story. The role of communication systems is to carry those stories across the emptiness, bridging the immense distances with invisible links. In keeping with the theme of quiet persistence, communications in space are often described as a gentle whisper, a beam of radio waves softly spreading out as it travels, containing precious data. These signals are typically very weak by the time they reach Earth, but with sensitive listening equipment, we hear them loud and clear. It's a testament to patient engineering that even a faint transmission, billions of kilometers away, can be captured and understood. On board a spacecraft, communication usually begins with an antenna pointing toward Earth. Many probes have high-gain antennas shaped like large shallow dishes. They are steered by motors to face our planet's direction, or where Earth will be when the signal arrives, accounting for travel time. When the spacecraft has something to send, perhaps a batch of images or readings, it encodes those into a radio signal. The transmission might last minutes or hours, a steady stream of ones and zeros translated into a modulated carrier wave. The power used is often just tens of watts, similar to a household light bulb, yet that signal will eventually span the breadth of the solar system. Back on Earth, we have our own marvel, the Deep Space Network, DSN, a set of giant radio antennas positioned around the globe in California, Spain, and Australia to maintain contact with distant spacecraft. Picture one of these antennas, a massive white dish, 70 meters across, slowly turning in a clear desert night, pointing at a patch of sky where a spacecraft's whisper is coming from. The night is quiet and still. The dish moves almost silently, driven by motors smooth enough to not jolt the delicate listening equipment. When the faint radio signal reaches Earth and touches the dish, it's reflected and focused onto a sensitive receiver. The energy of the signal is incredibly small now, trillionths of a watt, yet the equipment detects it and amplifies it. In a control room, represented by a line on a screen, the signal appears out of the background noise. What was once a lonely transmission in the void is now being heard. As the data flows in, it is processed and sent to mission centers where engineers and scientists await the latest news from their spacecraft. Perhaps it's a set of new photos of Saturn's rings or the latest status of a rover. The important thing is that the information has traversed the gulf of space unscathed, carried by radio waves that are themselves quiet and invisible. Sometimes communications involve relays. For example, a lander on Mars may send data up to an orbiter overhead, which then forwards the data to Earth. Each link in the chain operates methodically. The lander sends a signal during a scheduled overpass. The orbiter catches it and stores it, then turns its larger antenna toward Earth to beam it home. These relays ensure that even small robots with little antennas can get their messages out, using bigger spacecraft as stepping stones for their signals. Communication is a two-way conversation as well. When we need to send commands to a distant spacecraft, the process is equally patient. Engineers prepare a series of instructions, perhaps telling a probe to adjust course or instructing a rover to move to a new location. And those instructions are transmitted from Earth. Huge transmitters feed power into the DSN antenna, sending a strong beam toward the target. Across millions of kilometers, the spacecraft's antenna collects a few stray watts of that, and its onboard receiver decodes the commands. We trust that our message will arrive safely, sometimes only after hours of transit time. There is a gentle formality to this exchange, a daily or weekly check-in, a hello, how are you, here is what to do next, from Earth, followed by the spacecraft's report coming back. The communication network is the lifeline that keeps our exploration connected to us. It means that no matter how far our robotic explorers go, they are never truly alone. There is always an ear listening back home and a voice ready to speak to them. It might take patience. The echo of a command sent to Neptune may not return with data for many hours, but it rewards that patience with knowledge. In the stillness of a late night, an engineer might step outside and look at the sky, knowing that at that very moment, a distant spacecraft is sailing hundreds of millions of kilometers away, and yet a thread of radio waves links that spacecraft to the ground beneath their feet. Such thoughts emphasize how remarkable this quiet connection is, and how it binds our far-flung explorers to the human story. To traverse the immense ocean of space, spacecraft rely on navigation systems that combine all the technologies we've discussed: propulsion, sensors, communication, and autonomy into a guidance network. Navigating a spacecraft is a bit like navigating a ship at sea, but instead of waves and winds, there are gravitational fields and orbital mechanics. The process is deliberate and careful, plotted out often years in advance, yet requiring gentle course corrections along the way. Space navigation is a testament to precision and patience. At its core, it answers two fundamental questions: where am I, and where am I going? The answers are found using the stars, the planets, and the spacecraft's own subtle motions. A primary tool of navigation is observing the stars. Spacecraft often carry star trackers, which are special cameras that take pictures of the star field around the craft. The onboard computer compares these pictures with an internal star map to determine the spacecraft's orientation, a modern version of how ancient sailors used constellations to discern direction. In the silent blackness, a star tracker might snap an image every few seconds, each time the computer quietly updating its knowledge. I am rotated 5 degrees from where I should be. Let's adjust. Thrusters, or reaction wheels, then make the tiny adjustments to align the vehicle as intended. This constant referencing of the stars means the spacecraft always knows which way it is pointed, an essential part of knowing where to go next. Another aspect of navigation is measuring the spacecraft's motion through space. This is often done by communicating with Earth and using the data as a form of triangulation. As Earth-based antennas track the probe, they measure how long the signals take to travel, and even the subtle Doppler shift, the slight change in frequency due to motion. These measurements allow navigators to calculate the spacecraft's exact distance and speed relative to Earth. Picture a spacecraft coasting between planets. It might seem to just be drifting, but it is actually moving at tens of thousands of kilometers per hour. Each day, navigators receive timing data from the communications link and can tell if the spacecraft is a little ahead or behind its expected position. If a correction is needed, they plan a trajectory correction maneuver. This maneuver is typically a brief firing of thrusters or an engine burn, perhaps days or weeks in the future. The commands are uplinked, and when the moment comes, the spacecraft's autonomous systems carry it out. A short burst, maybe a few centimeters per second change in velocity, executed perfectly in the void. Afterwards, the probe is on a slightly adjusted path that will, months later, result in it arriving exactly where it needs to be, say, at a point in space where a planet will also arrive, enabling a flyby or orbital insertion. Space navigation also involves the gentle art of orbital mechanics around other worlds. When a spacecraft arrives at a planet, it often needs to enter orbit or prepare for landing. This is done by carefully timing engine burns. For example, when a spacecraft arrives at Mars to orbit it, the navigation team plans an orbital insertion burn. The spacecraft turns so that its main engine faces forward against its direction of travel and ignites it while approaching the planet. This slows the spacecraft just enough for Mars's gravity to capture it. The burn might last only 20 minutes or so, during which the communication might be curtailed as the spacecraft focuses on the maneuver. Once complete, the craft is in a stable orbit, gently falling around the planet rather than flying past it. All of this requires immense precision. Too long a burn, and the craft could descend too low. Too short, and it might miss orbit. Yet with careful calculations and reliable technology, it works routinely. And it's done with a sort of cosmic patience. The spacecraft may have travelled for half a year to reach Mars, and now it calmly conducts this final step to become a new artificial moon of that world. Perhaps one of the most poetic aspects of space navigation is the use of gravity assists, as mentioned earlier. This is navigation by cooperation with nature. Mission designers plot a course where a spacecraft will swing past a planet or moon at just the right distance and angle. The gravity of that body will tug on the spacecraft, changing its direction and speed. No engine is fired. Instead, the navigators borrow energy from the planet's orbital motion. It's a quiet tug, invisible except through its effect. The spacecraft leaves, now on a new trajectory that might take it further and faster than before. The famous Voyager missions used multiple gravity assists, flitting from one giant planet to the next, each time being flung onward, like a dancer taking hands with a partner, spinning, and then being launched toward the next partner. During these slingshot maneuvers, the spacecraft simply coasts. To any instruments on board, nothing special might be sensed except a change in the path. But the path is forever changed, a grand arc redirected, and all accomplished through timing and careful aim. In every phase of a mission, navigation is the quiet guide that ensures we reach our intended destinations. It's the combination of human planning and machine execution, played out over months and years. We often personify spacecraft as explorers, but we could just as easily imagine the navigation itself as a devoted navigator charting a course through unknown seas. There is a deep reassurance in how methodical it is. Check the stars, adjust orientation, consult the ground, refine the path, repeat. Like a heartbeat or a breath, these cycles continue throughout the life of a mission. They carry our hopes and our instruments to places we have never been, and bring them safely through complex journeys. In the stillness of the cosmos, navigation provides direction and purpose, one gentle step at a time. Each of the systems we've explored, launch vehicles, propulsion engines, life support, robotics, solar panels, sensors, autonomy, communications, and navigation, plays a distinct and vital role in the theatre of space exploration. Yet they do not operate in isolation. They are like instruments in an orchestra, each contributing its part to a larger symphony of exploration. When a mission is underway, all these technologies function together seamlessly. As a spacecraft cruises millions of kilometers from Earth, Its solar panels quietly feed power to life support or instruments. Its autonomous brain keeps it on course using navigation data and fires a tiny thruster as needed. Its sensors gather data, and its antenna points home to deliver the findings. Everything is interlinked. Without power, the sensors cannot observe. Without navigation, the propulsion would not know when to adjust. Without communications, the treasure of data would never reach us. Through precise engineering and thoughtful design, these components support one another, creating something greater than the sum of their parts. A self-contained explorer capable of braving the void. Consider for a moment the journey of a hypothetical space probe, traveling to the edge of our solar system. It began with a thundering launch that lifted it beyond Earth's cradle. In space, it unfolded its solar panels and turned on its instruments. For years, it has been coasting outward. There were occasional course corrections, each one computed by navigation, executed by propulsion, and overseen by autonomy. The probe's onboard heater kept its electronics warm as the sunlight grew faint, and eventually the radioisotope generator took over to provide power when solar panels no longer sufficed. The robotic instruments kept scanning the environment, perhaps discovering new insights about the heliosphere or interstellar space. Throughout, it maintained a communications schedule. Maybe once a week, it pointed its antenna to Earth and sent back a report. On Earth, engineers listened and marveled at how far their creation had gone, yet was still functioning perfectly. This tiny traveler carries with it all the trust we've placed in our technology. Trust that it will keep itself safe, that it will phone home, that it will do the science it was sent to do. And if you look at it piece by piece, that trust is well founded. Each subsystem is built with redundancy and care, each thoroughly tested to operate in the quiet vacuum, far from repair. The spacecraft becomes a harmonious ensemble, a reliable and persistent presence journeying through the unknown. As we conclude this gentle exploration of spacefaring technologies, we can appreciate not only the individual marvels, but also their collective resilience. Space is unforgiving, yet through ingenuity, we have crafted tools that thrive there calmly. They don't conquer space with brute force. Instead, they endure with grace. Like a candle shielded in a lantern against the wind, our spacecraft systems protect the flame of exploration, keeping it burning steadily. In the silent ballet of a probe orbiting a distant moon or a rover crossing a crater, we witness the triumph of patient engineering. It's inspiring to realize that these machines, built by human hands, now operate on their own far away, carrying a piece of our presence with them. Our journey through these technologies has been one of quiet wonder. We've seen how each gear and circuit quietly does its duty to support the grand adventure of exploring the cosmos. With this understanding, we find a certain peace of mind, knowing that when we send out voyagers into the dark, they are equipped with the very best of our steady, enduring innovations. They are never truly alone out there, for they carry with them the care and brilliance of those who built them. And they remain in touch through the faint radio whispers that bridge space. Now, as we drift toward the next chapter of our Odyssey, we carry forward a newfound appreciation for the backstage heroes of space travel. The technologies that make exploration possible will continue to hum in the background, reliably doing their work as we turn our attention to whatever lies ahead. In the next part of our journey, we will continue to follow this cosmic trail, confident and calm, supported by the quiet strength of these marvels. With the faint glow of distant starlight guiding us and the steady pulse of our spacecraft accompanying us, we gently invite you to continue onward into the boundless night, where more wonders await. The voyage continues, one calm step at a time, into the vastness of space. Humanity has always gazed upward, captivated by the faint glow of stars scattered gently across the night sky. These distant lights, suspended calmly in the cosmic darkness, stir something deep within us, a quiet longing to venture beyond our home and journey toward other suns. The stars represent both a limit and a promise, a boundary marking our current horizon of knowledge, and a serene invitation to reach beyond. Interstellar travel, the peaceful yet profound concept of voyaging from one star to another, embodies humanity's gentle but persistent desire to explore the farthest reaches imaginable. Yet the journey between stars is unlike anything we have experienced. Even the nearest stars exist at distances so vast they challenge our sense of scale. The closest star system, Alpha Centauri, sits quietly 4¼ light years away. Light itself, moving at the universe's greatest speed, takes over 4 years to bridge this gap. For human-made spacecraft, traveling even thousands of times slower than light, such a voyage could require decades, centuries, or even millennia. These immense spans of space and time gently remind us of the limits we face, yet they also encourage us to patiently dream, to ponder the quiet determination and innovation required to someday traverse the gulf between stars. Long ago, at the edge of our solar system, 2 quiet ambassadors from Earth began a patient journey into the infinite night. The Voyager spacecraft, launched in the 1970s, were originally tasked with studying Jupiter and Saturn. After accomplishing their primary mission, these silent messengers kept traveling outward, driven by momentum gained from their planetary encounters. Today, after more than 4 decades, Voyager 1 and Voyager 2 glide softly through the boundary region, where the sun's influence gives way to interstellar space, a serene transition from the warm solar winds into the cool stillness beyond. In the calm darkness of interstellar space, the Voyagers are profoundly alone, far from their creators, yet gently communicating with Earth through whispers of radio signals. Those faint signals, traveling at the speed of light, take hours to reach us, crossing billions of kilometers of empty space. Although their scientific instruments gradually shut down as power diminishes, the Voyagers continue their quiet drift, carrying golden records etched with sounds, images, and greetings from humanity. These records are not intended to reach another civilization anytime soon. Rather, they symbolize a poetic gesture, a hopeful whisper into the cosmic void that we exist and have dreamed of exploring the stars. Voyager's slow voyage demonstrates the immense distances that define interstellar travel. Even after more than 40 years, Voyager 1, humanity's most distant traveler, is only a fraction of the way to the nearest star. At its current speed, it would take tens of thousands of years to approach another stellar system. The Voyager's ongoing journey into the silence of interstellar space is a gentle reminder of our place in the universe and the patient dedication required to explore beyond the familiar. The challenge of interstellar travel lies not only in distance, but also in speed. Traditional chemical rockets, which have carried astronauts and robots around our solar system, are inadequate for journeys spanning multiple light years. Even our fastest spacecraft travel thousands of times slower than the speed of light. To truly contemplate interstellar exploration, we must dream quietly of other propulsion technologies, ideas that could, one day, gently propel us between stars. One subtle concept is the solar sail, a vast, reflective sail pushed forward by the gentle pressure of photons from the sun, or even powerful lasers directed from Earth. A solar sail harnesses nothing but light itself to accelerate. And while its acceleration is incredibly soft, it is continuous. Given enough patience and time, A solar sail spacecraft could reach significant fractions of the speed of light. Imagine a delicate structure, thin as a whisper, expanding gracefully in the void like a flower, unfolding slowly in space, gaining speed, imperceptibly, yet persistently, day after day. Over decades, such a sail could quietly reach speeds, allowing it to travel to nearby stars within a human lifetime. Another peaceful, futuristic vision involves spacecraft propelled by nuclear fusion engines. Engines powered by the same process that softly illuminates the stars themselves. Fusion propulsion could gently accelerate a spacecraft to substantial fractions of the speed of light, shortening voyages between stars to decades rather than centuries. These imagined vessels would cruise smoothly through space, sustained by the calm yet potent fusion reactions on board. The interior of such a craft would resemble a tiny world, a tranquil refuge drifting through darkness, self-contained and self-sustaining, patiently traversing the void between distant suns. Even more speculative, yet still fascinating, are ideas such as antimatter propulsion, harnessing energies far greater than conventional methods. Such concepts remain quietly theoretical, but they illustrate the breadth of imagination inspired by interstellar exploration. Each idea gently expands our sense of what might be possible, encouraging patience as we wait for technologies and understanding to mature. If reaching another star system takes centuries, we confront a quiet but profound question. Could humans embark on a voyage whose destination is beyond the lifespan of any single traveler? This question leads us gently to the idea of generation ships, enormous, self-contained spacecraft designed for voyages lasting hundreds or even thousands of years. These ships would carry entire communities, generations born and raised among the stars, their lives unfolding entirely within the vessel. Each generation would patiently pass the mission onward, slowly approaching their distant goal. Picture such a craft, drifting serenely through deep space. Inside its walls, a tranquil ecosystem might flourish, a garden of plants and trees, providing food and oxygen, recycling water and nutrients in a perpetual cycle. People would live quiet lives, knowing their purpose is to bridge a vast span of time and distance, holding gently to traditions and knowledge, passing down memories and dreams of a world they had never personally known. Their lives, though confined to the ship, would be meaningful, connected deeply to the mission's grand narrative. Generations would quietly rise and pass, guided by a shared hope and a calm sense of duty, inching closer, year by year, toward another star's distant light. Such a voyage poses gentle philosophical questions. Would those born on board share their ancestors' desire to reach the final destination? Would the destination become almost mythical, a distant promise that quietly shapes their culture and purpose? These questions remind us of the profound commitment that interstellar travel demands. Beyond technology, it requires the gentle strength of human resilience, continuity, and purpose. Beyond technical and philosophical questions lie quiet ethical considerations. If a generation ship were possible, should we send people on a journey they themselves did not choose? Could we responsibly design an environment that sustains not just biological life, but human happiness and well-being for generations? There is a peaceful humility required to engage these questions, a recognition that interstellar travel is more than physics and engineering. It is also a deeply human endeavor, calling forth our best qualities of empathy, care, and foresight. A mission spanning centuries would require gentle stewardship, a commitment to the welfare of generations yet unborn. This quiet ethical dimension enriches our understanding of exploration, reminding us that every voyage into space carries with it profound responsibilities, deeply rooted in compassion and mindfulness. In lieu of physical travel, humanity has also sent gentle messages toward the stars. Radio signals, like quiet whispers, travel outward from Earth at the speed of light, silently carrying broadcasts that expand into space, slowly diffusing across the vast distances. If any distant civilization could detect and decipher these signals, they would find the faint echoes of our presence, a mosaic of sounds, images, and encoded knowledge drifting softly through space. Yet even radio messages take years or decades to reach nearby stars, and their faintness diminishes rapidly with distance. The act of sending messages, then, becomes symbolic, a patient gesture of openness toward an unknown cosmos, a quiet affirmation that humanity seeks connection and understanding across the void. This practice gently reinforces our identity as explorers, not just of space, but of possibility itself. For now, interstellar travel remains gently beyond our immediate reach. Yet our efforts continue with patient determination. Scientists and engineers around the world quietly develop propulsion technologies, study the psychology of long-duration space travel, and ponder philosophical questions that will shape future journeys. Small, experimental spacecraft, like the Breakthrough Starshot concept, propose tiny probes accelerated by powerful lasers, offering glimpses of how our first robotic emissaries might travel gently between the stars within our lifetimes. These incremental steps softly remind us that interstellar exploration is not an urgent dash, but a calm, deliberate journey. The stars will wait, as they always have, shining quietly in the night sky, inviting our patient exploration. Humanity's longing to travel among them will persist, quietly sustained by imagination, innovation, and determination. As we conclude this meditative reflection, we pause gently at the threshold of what is currently possible. Interstellar travel invites us not to rush forward, but to contemplate patiently, to dream softly, imagining the quiet strength and humility required for voyages spanning generations and distances far beyond our daily lives. It reminds us that true exploration is a patient conversation with the unknown, undertaken with care, courage, and quiet reverence. In pondering the limits of exploration, we discover new perspectives on our own humanity. The immense distances and timescales involved in interstellar travel offer us a serene context in which to see ourselves more clearly. As a species capable of looking forward with hope and wonder, gently carrying dreams of exploration through generations. And perhaps, in time, those gentle dreams will softly carry humanity itself to distant stars. With this peaceful reflection, our journey continues, gently inviting you forward into the cosmos, patiently, calmly, one thoughtful step at a time. Imagine drifting far away from our familiar cosmic neighborhood, passing countless galaxies as we journey into the silent depths of space. As we travel outward, the stars thin out and the darkness deepens, enveloped by a serene stillness. Eventually, even the last faint glimmers of distant galaxies behind us seem to disappear, and ahead lies darkness where no star's light has yet reached us. In this tranquil darkness, we approach a boundary, not marked by any wall or barrier, but by the simple fact that beyond it, light has not yet arrived. This is the edge of the observable universe, our cosmic horizon. This horizon is not a physical edge with an end to space, but rather a gentle limit to how far we can see. Just like standing on a calm ocean shore, seeing the water meet the sky at the horizon, we know there is more ocean beyond that line of sight. In the same way, when we gaze into the universe, our view is bounded by a cosmic horizon, beyond which the universe continues unseen. It is a horizon of light and time, set by the finite speed of light and the age of the universe itself. Even within this observable realm, the cosmos is breathtakingly vast. It contains hundreds of billions of galaxies strewn across tens of billions of light years of space. Yet all of that is still only what we are able to see. Like the ocean extending beyond the curve of the Earth, there is almost certainly far more universe beyond our sight, waiting quietly beyond this horizon. The universe reveals its story to us through light, which travels at a fixed, finite speed. When we look at a distant star or galaxy, we are not seeing it as it is now, but as it was when its light began the long journey to us. Light is like a cosmic messenger, carrying images of the past across the vast expanse. The farther away an object lies, the longer its light has travelled, and the older the image we receive. In this way, looking deeper into space is like looking back in time, peering into epochs long gone. Even the gentle sunlight that warms our skin is actually an 8-minute-old memory of the sun, the time it took for those rays to cross the space between. Extend this idea to the stars of the night sky. Some of their light has been travelling for decades, centuries, or thousands of years before it reaches our eyes. The nearest large galaxy, Andromeda, is so distant that its light takes over 2 million years to arrive. We see it now, as it was long before any human ever gazed up at the night sky. And for the most remote galaxies we can detect, their faint glow has journeyed across space for billions of years. We are catching glimpses of those galaxies as they were eons ago, preserving cosmic history in each delicate ray. Out in the cosmos, distance and time are deeply entwined. As we look farther and farther away, deeper into the past, we approach the very dawn of the cosmos. Eventually we reach a point where galaxies themselves vanish from view, and all that remains is a soft, all-encompassing glow. This is the cosmic microwave background, a gentle bath of light that fills the sky in every direction. Though invisible to our eyes, if we had microwave vision, the entire sky would appear awash in a faint, cool glow. It is the oldest light we can see, a quiet afterglow from a time when the universe was just a newborn, only a few 100,000 years old. In those early times, the universe was a hot, bright fog of particles and energy all mingled together. As it expanded and cooled, space became transparent, and light was finally free to travel unimpeded. That primordial light has been journeying for over 13 billion years, stretching and softening into microwaves as space expanded. What we detect now is that ancient light's whisper, a nearly uniform glow that tells of the universe's first moments after birth. It surrounds us like a gentle echo of creation, reminding us how far our vision has extended through time. This cosmic background is like a luminous veil at the edge of our sight. Beyond it, the extremely early universe remains hidden, with no direct light to show us its form. When we observe a distant galaxy near the edge of our view, its light does more than show us the past. It also carries subtle clues to its distance. One of these clues is the light's color. As the universe expands, the space between us and faraway galaxies stretches, and so do the light waves traveling through that space. This makes the light appear redder than it originally was, a phenomenon known as redshift. The greater the distance and the longer the journey the light has made, the more pronounced this reddening becomes. Astronomers carefully measure these shifts in color like a cosmic code to estimate just how far away these remote galaxies are. In addition to the color of the light, there are other gentle techniques to gauge distance. Some stars and stellar events act as standard candles because we understand their true brightness. For example, certain types of pulsating stars rhythmically dim and brighten in a way that reveals their intrinsic luminosity, and stars that end their lives in a radiant finale known as a supernova shine, with a predictable brilliance we can recognize. By comparing how bright these known lights appear from Earth with how bright we believe they truly are, astronomers can infer their immense distances. It is akin to spotting a distant lighthouse across a dark sea. If its light is faint, you know it must be very far away. Using these methods together, we map the distances to galaxies nearing the limits of the observable universe. Each measurement, a careful step farther into the unknown. Each new yardstick of distance extends our cosmic map, pushing the frontier of the known universe a little farther out. Our observable universe is intimately tied to the history of the universe's expansion. Since the moment of the Big Bang, space itself has been stretching and growing. Galaxies are not sailing on a static sea. Rather, the space between them is expanding, carrying them apart like driftwood on a slow-moving tide. Over billions of years, this expansion has broadened our cosmic horizon, allowing light from more distant regions to finally arrive. As the universe ages, this horizon gradually extends outward, like a rising sun, revealing more of a vast landscape. Yet even with infinite time ahead, there will remain parts of the universe so far away that their light will never reach us, forever beyond the horizon of what we can observe. In the first fleeting fraction of a second after the Big Bang, cosmologists theorize that the universe underwent an extraordinary event called inflation, a sudden, exponential expansion. During this brief moment, the fabric of space ballooned dramatically, far faster than light could travel. This means that regions of the universe that were once close together were rapidly pushed far apart, beyond each other's observable reach. As a result, the universe we see, immense as it is, may be only a tiny patch of an unimaginably larger whole. This early inflation planted the seeds of all cosmic structures and ensured that distant parts of the cosmos would share similar properties. Our observable universe could be like a single calm eddy in a boundless ocean, one part of a grander cosmos that extends far beyond our cosmic horizon. The observable universe itself is enormous and rich. Astronomers estimate it spans roughly 93 billion light-years across, filled with hundreds of billions of galaxies. Each of those galaxies is a vast system of stars, many with their own planets, all shining through the darkness of space. And yet, everything within this immense volume is just what is accessible to us. We are like observers standing in a quiet clearing, surrounded by fog. We can see only so far through the mist. Beyond our clearing, the landscape continues, but it remains hidden from our eyes. Similarly, our view of the universe has a limit, not because the cosmos ends there, but because the light from more distant realms has not reached us, and perhaps never will. There is comfort in thinking that beyond this horizon, the cosmos continues with more galaxies, more stars, and wonders we have yet to dream of, stretching onward through the silence. Our cosmic horizon is both a boundary and a gentle reminder, a reminder of how much more lies out there, resting quietly beyond the edge of our understanding. When we peer at galaxies near the edge of the observable universe, we are looking deep into cosmic history. These faint, distant smudges of light are images of the universe when it was young. In the present day, those galaxies might be large and mature, or they might have merged into new forms. But we see them as they were billions of years ago, frozen in time by their great distance. This gives us a rare opportunity to study how galaxies looked and behaved in the early eras of the cosmos. It is as if we have old photographs of the universe's childhood, snapshots from a time long before our sun and earth existed. In a sense, we become cosmic archaeologists, unearthing the history of the universe preserved in the light of distant stars and galaxies. With each improvement in our instruments, this window into the past grows clearer and wider. The Hubble Space Telescope, for example, revealed some of the most distant galaxies then known, showing us light from when the universe was only a tenth of its current age. Now, the James Webb Space Telescope is peering even further, detecting the faint glow of galaxies that formed just a few 100 million years after the Big Bang. Each deeper observation is like discovering an even older record in a cosmic archive, bringing us closer to witnessing the universe's first light. By collecting these ancient galactic memories, astronomers piece together a timeline of cosmic evolution. Nearby galaxies show us the universe in its adulthood, rich with heavy elements and billions of stars. Galaxies a bit farther out reveal a younger universe, where stars are just beginning to forge those heavier elements. Travelling farther still, out near the frontier of visibility, we find galaxies in their infancy, small and irregular, just beginning to form cohesive structures. We witness the cosmos when it was only a fraction of its current age, during an era often called the Cosmic Dawn, when the first generations of stars and galaxies brought light to the darkness. Each increase in distance is like a deeper layer of time, unveiling how the peaceful cosmic ocean we know gradually took shape from more restless beginnings. The most distant galaxies ever observed are incredibly faint, their light stretched to infrared wavelengths by billions of years of travel. Through our most powerful telescopes, we can barely discern their shapes. Often they appear as tiny, dim specks of light. Yet within those humble specks lies the story of the first structures in the universe. They show us that even in those early times, gravity was gently drawing matter together, forming stars and clusters that would eventually grow into larger galaxies. We see hints that the seeds of modern galaxies were already planted in that primordial era, like small islands of light in a vast, dark sea. Observing these ghostly young galaxies helps confirm our theories of how structure formed, illuminating the path by which the cosmos grew from a smooth, hot beginning into the richly textured cosmic tapestry we see around us today. Standing at the edge of the observable universe in our mind's eye, we find ourselves faced with both knowledge and mystery. Everything we have learned about the cosmos, its age, its vast scale, its composition, comes from this one visible region of space and time. We operate under the assumption that the laws of physics and the broad patterns we observe here hold true everywhere, even beyond our sight. The remarkably even glow of the cosmic microwave background, for instance, suggests that far-flung regions we cannot see are not drastically different from the portion we can observe. Yet we must remember that our understanding is bounded by what light has told us. There may be surprises waiting quietly beyond our observational reach, realms that remain forever hidden because the universe has not given us their light. This horizon of ours teaches us humility. It reminds us that no matter how advanced our instruments become, there will always be a boundary to our cosmic knowledge, a horizon we cannot cross by observation alone. Instead of seeing it as a hard stop, we can embrace it as a gentle inspiration for wonder. Knowing that there is more than we can ever see fills us with a quiet awe and perspective. Our place in the cosmos, vast as it is part of a mystery that stretches far beyond us. It is as if we have read only a few chapters of an endless book. The chapters we have finished are beautiful and enlightening, and we know countless more remain beyond the edge of our perception. We cannot read those unseen chapters, but it is comforting to know they are there. In the peaceful darkness beyond our cosmic horizon lies the great unknown. Rather than a darkness to fear, it can be soothing to realize that the universe holds secrets we have yet to discover. There is a gentle beauty in not having all the answers, in knowing that some questions will always remain open, allowing our curiosity and imagination to roam free. Just as the night sky is calming, even when clouds hide some stars, the unseen parts of the universe can comfort us simply by existing, silent and mysterious. The unknown is not emptiness. It is a promise of endless discovery, a quiet invitation to keep exploring in mind and spirit. As we conclude this chapter of our cosmic journey, we linger for a moment at the edge of what we can see and know. Here, on the border between the known and the unknowable, we feel the depth and serenity of the cosmos. We have traveled from our local neighborhood of stars to the soft afterglow of the Big Bang, moving ever outward in space and time along the way. Our journey is not over. There are more wonders ahead. When you are ready to continue, we will gently venture onward. In the next part of our journey, we will step beyond this horizon we have reached, continuing to explore the endless mysteries of space. We invite you to join us again in part 11, as our voyage through the cosmos carries us farther into the unknown, guided by the same calm curiosity that has brought us this far. Time in the universe stretches beyond ordinary imagination, flowing gently from the moment of the Big Bang to the present day. In the stillness of space, time is like a slow river, carrying the story of galaxies, stars, and planets across nearly 14 billion years. We begin this part of our journey by contemplating cosmic time, the vast ocean of moments since the universe first blinked into existence. It's a concept so grand that our everyday experience can barely grasp it, yet we can sense the mystery and magnitude it holds. Cosmic time is the timeline of everything, from the birth of the first light to the formation of galaxies, and all the quiet epochs in between. Astronomers tell us that the universe is approximately 13.8 billion years old, a number beyond easy comprehension. Imagine compressing that entire span into a single year. In this cosmic year, all of human history would flicker only in the final moments of the final day. Such is the scale of deep time, where billions of years flow as effortlessly as seconds in cosmic perspective. It's a gentle reminder of our humble place in a timeline so immense and ancient. The Big Bang can be thought of as the dawn of time itself, the starting point of the cosmic clock. Before that moment, time as we understand it may not have existed. It's as if time was born along with space and energy in that primordial event. Ever since, the cosmic clock has been steadily ticking, marking the expansion and unfolding of the universe. We picture this not as a loud ticking, but as a quiet, persistent rhythm, a cosmic heartbeat that has pulsed for eons. In this vast timeline, galaxies swirl and stars live and die in slow motion. Light from distant galaxies has traveled for millions or even billions of years to reach us here on Earth. When we look up at the night sky, we are witnessing the past. The stars we see might have begun their journey toward our eyes long before we existed. Starlight is ancient, and in its soft glow we feel connected to deep time, as if we are time travelers, peering across ages with each glance at the cosmos. Time, in our everyday lives, feels steady and uniform. Seconds turn into minutes, minutes into hours, all at a familiar pace. We set our clocks by this seemingly constant beat. However, in the early 20th century, a quiet revolution in physics revealed that time is not as rigid as we once thought. Albert Einstein's theory of relativity introduced a profound idea. Time can stretch and compress, flowing differently depending on conditions like speed and gravity. It's a mysterious concept, but we can approach it calmly, step by step, like walking through a silent, starry night of ideas. Imagine identical twins. One twin remains on Earth, while the other embarks on a high-speed journey through space, moving at a significant fraction of the speed of light. For the traveling twin, the adventure might last only a few years. But when that twin returns home, they discover their sibling on Earth has aged by decades. This scenario, known as the twin paradox, illustrates time dilation. Time has flowed more slowly for the fast-moving twin. To the spacefarer, those years felt normal. Time always feels normal to the one experiencing it. But compared to their twin, far less time passed. It may sound like science fiction, but this effect is real, predicted by Einstein's special relativity and confirmed by experiments. In everyday life, these differences in the flow of time are incredibly tiny. For the speeds we move, in cars, planes, or even rockets, the time dilation amounts to barely a flicker of a second over a lifetime. Only when moving at truly extreme speeds, close to the speed of light, do these changes become dramatic. So, in our day-to-day experience, we hardly notice time's flexibility. Yet just knowing it's there gives us a sense of wonder, as if time has hidden elasticity that only reveals itself under extraordinary conditions. Einstein's insights didn't stop at speed. He also realized that gravity, the force that holds planets in orbit and binds us to Earth, can affect the flow of time. This is the essence of general relativity, which describes gravity not just as a pull, but as a bending of space and time. In regions of stronger gravity, time runs a bit slower. Where gravity is weaker, time runs a bit faster, as seen by an outside observer. It's another gentle peculiarity of the universe. Gravity and time entwined in a subtle cosmic dance. We can imagine a simple scenario to feel this idea. Picture two identical clocks. One is set at sea level by the ocean, and the other on a high mountaintop. The clock at sea level is in a stronger gravitational field closer to Earth's massive bulk than the clock on the mountain. If we let them run and later compare them, the mountain clock will show ever so slightly more time elapsed. Time on the mountaintop runs just a touch faster than time at sea level. The difference is tiny, far too small for us to notice without sensitive instruments. But it's real. Gravity subtly shifts the pace of time. Now consider a place where gravity is extremely strong, a black hole. Near a black hole, the warping of space and time is so intense that time itself slows dramatically relative to the outside universe. If you could hover safely near a black hole, you might experience only a short time passing, while, far away, years or centuries could go by. At the very edge of a black hole, a boundary called the event horizon, the effect becomes even more extreme. To a distant observer, an object falling toward the event horizon would appear to slow down and almost freeze in time at that boundary. From the falling object's own perspective, time would continue normally, but we on the outside would seemingly never see it finish its fall. Such is the strange nature of time near a massive object. What is a brief moment close up can be nearly an eternity from afar. These ideas of time dilation might sound abstract, but they have practical effects even here on Earth. One fascinating example is the GPS satellites that orbit our planet. Each satellite carries an extremely precise clock. Because these satellites are moving fast and are higher above Earth's surface, their clocks tick at a slightly different rate than clocks on the ground. The speed makes their time run a little slower, as per special relativity, and the weaker gravity up there makes their time run a little faster, as per general relativity. Engineers must account for these tiny differences. If they didn't, the GPS navigation on your phone or car would drift off course by miles. So each day, tiny adjustments are made to synchronize satellite time with Earth time. It's a quiet marvel that something as routine as getting directions relies on understanding that time can bend ever so slightly. Scientists have also performed experiments to show this flexibility of time. In one famous test, atomic clocks were flown on airplanes around the world. When compared to clocks that stayed on the ground, the airborne clocks had ticked just a little slower, exactly as relativity predicted. These effects are nothing you would ever feel. They are measured in microseconds, but they confirm a profound truth. Time is not absolute. It flows differently under different conditions, even if we only notice it under extreme circumstances or with precise instruments. Understanding this pliability of time gives us a sense of the gentle, hidden intricacy in the cosmos, a reassurance that reality has layers of wonder quietly at play. Relativity reveals how time can stretch and bend in extraordinary situations, but there is another perspective of time that is equally awe-inspiring. This is the realm of deep time, the immense spans of ages over which the cosmos evolves. Now, let us drift into that vast ocean of time where millions and billions of years are the chapters of the universe's story. The age of the universe, nearly 14 billion years, is our first taste of deep time. Across that expanse, the cosmos has undergone remarkable changes. There was the blazing birth of the first stars, the gathering of those stars into young galaxies, and the formation of planetary systems. Generations of stars have lived and died, each enriching the cosmic gas with new elements, seeding the potential for planets and life. On at least one small blue planet, billions of years of gradual change eventually gave rise to living beings who can look up and contemplate it all. We can think of the universe's history as having chapters: the fiery beginning, the age of galaxies taking shape, the long middle era of starlight and cosmic growth, and the current epoch in which we exist and wonder. Think of a star's life as a slow, graceful arc of time. A star, like our sun, shines steadily for about 10 billion years. For most of that time, it quietly fuses hydrogen into helium in its core, a beacon of light and warmth in the darkness. To us, even a single year can feel significant, and a century is nearly beyond one person's experience. Yet the sun will continue to shine almost unchanging for countless generations of humans, billions of sunrises and sunsets, before it even begins to grow old. In its final stages, eons from now, our sun will swell into a red giant, gently shedding its outer layers into space. It will then settle down as a small white dwarf star, glowing softly with residual heat for billions more years. This entire saga spans a vast stretch of time, a cosmic story unfolding in slow motion. More massive stars live faster, more dramatic lives. A star many times heavier than the sun may burn through its fuel in just a few million years. A brief flash in cosmic terms. Such a star might end its life in a supernova explosion. In that final act, it forges heavy elements and scatters them into space. Those materials will drift in the galaxy, eventually becoming part of new stars, new planets, and perhaps new life. The calcium in our bones and the iron in our blood were created in such stars long before the Earth existed. In this way, the cycle of starlight and star death links us to the deep past. We carry a bit of that ancient cosmic history within us. On an even larger scale, galaxies themselves change over immense periods of time. Our own Milky Way galaxy and the neighbouring Andromeda galaxy are drifting toward each other in a very slow embrace. In about 4 billion years, a span of time almost too vast to imagine, they will begin to merge. When that happens, it won't be a sudden crash, but a gradual intermingling. Stars from each galaxy will start to mingle like two gentle streams merging into a river, mostly passing by one another due to the great distances between them. Over additional billions of years, the two galaxies will become one. A new, larger galaxy formed from their union. It's a slow dance of galaxies, a cosmic waltz unfolding over eons. No single human lifetime could witness more than a tiny part of this dance, yet it will progress surely and serenely through deep time. Time in the universe has its rhythms and cycles, many of which we experience in our own lives. Consider the cycles close to home. The rotation of the Earth brings the rhythm of day and night, and the orbit of the Moon gives us the changing phases each month. Earth's journey around the Sun defines our year and the progression of seasons. These cosmic motions provide a natural clock for life on Earth. They are regular and comforting. A cosmic lullaby that has guided living creatures for ages. Since ancient times, humans have lived in harmony with these rhythms. We rise with the dawn and rest at night. We mark the seasons, planting in spring and harvesting in autumn, following the celestial dance. Each birthday we celebrate marks another full orbit around the sun, tying our personal milestones to the motions of the heavens. Even the moon that shone on our distant ancestors still waxes and wanes above us, connecting us through time to all who have gazed at its gentle light. Beyond our planet, the rhythms continue on larger scales. Our solar system itself orbits the center of the Milky Way galaxy. One such galactic orbit takes on the order of 230 million years. In fact, the last time the Sun was in this region of its galactic path, dinosaurs walked on Earth. It's amazing to imagine. As we live out our days and years, we are also passengers on this incredibly slow carousel, circling the galaxy in a journey so vast it transcends human history. In the stillness of this moment, let's gently reflect on what time means for us and for the universe. Time is the canvas on which all stories are painted. Without time, nothing could change or grow. Stars would not shine, planets would not orbit, and no life could unfold. Because time flows forward, the cosmos can have a history, and we can have our experiences. When we consider the enormity of cosmic time, it can put our daily lives into perspective. The universe has patience beyond comprehension, moving through cycles of creation and transformation that span billions of years. Reflecting on this vast steadiness can be comforting, reminding us that many of our worries are temporary and that we are part of a much larger, enduring picture. And yet, our awareness of deep time also highlights how precious each moment is. Our lives flash by in comparison to the age of a star or a galaxy, but that very brevity gives meaning to every sunrise, every laugh, and every memory we create. Each moment, once past, becomes unique in the tapestry of time, never to occur in exactly the same way again. Ultimately, time gives meaning to our journey, both in space and in life. It is the medium through which change becomes possible, the flowing river that carries us from what was to what is, and onward to what will be. In the vast expanse of cosmic time, our individual lives may be brief, but they are not insignificant. We are made of cosmic material, connected to the stars, and we are participants in the universe's story, even if only for a short chapter. That realization is humbling, as it shows how small we are on the scale of eons, but it's also profoundly uplifting, because it means we belong to something grand and enduring. Right now, as we breathe in this very moment, we are part of the universe's ongoing narrative. We can take comfort and wonder in that thought. As we conclude this part of our journey, let's sit for a moment in the quiet now, feeling the gentle passage of time. The past, present, and future are all connected in the continuum of time. We are a part of that continuum, however briefly. Whenever you feel ready, we invite you to join us for part 12, the final chapter of this cosmic journey. There, we will gently conclude our exploration and reflect on all that we have discovered. For now, take your time. There is no rush at all. The cosmos moves at a patient pace, and you can move at your own. When it suits you, let us continue to the final part of this soothing voyage through space and time. In the stillness of a starry night, we find ourselves gazing upward and imagining the future. Humanity stands at the gentle threshold of a new chapter among the stars, one written with hope, curiosity, and patient determination. In this final part of our journey, we contemplate the path ahead, a calm and steady adventure into the unknown, where new homes, new partnerships, and an enduring sense of wonder await us in the cosmos. High above Earth, a human presence already thrives aboard the International Space Station, a home in orbit where people live and work beyond their native world. As we look to the future, we envision expanding this idea into larger, long-term space habitats. These might be spacious stations orbiting Earth or other planets, slowly rotating to provide a gentle sense of gravity. Inside, astronauts could tend small green gardens and watch water droplets drift like tiny worlds as they gaze through wide windows at the blue glow of Earth or the dusty face of Mars. Someday, such a station might even hold a tiny park or pond, a small slice of Earth orbiting in the sky. On the Moon, We foresee safe havens for life taking root on the grey frontier, in habitats tucked into crater rims or buried under lunar soil for protection. People will build their first off-world homes. Soft lights glow in a domed greenhouse as explorers gather to share a meal of homegrown food. The moon's weak gravity makes each step feel gentle and light, a reminder of how different this world is. These first lunar dwellings may be small, a handful of connected modules, but they mark the beginning of a lasting human presence. Over time, an outpost could grow into a small village linked by tunnels, with laboratories, living quarters, and windows to gaze at Earth hanging in a black sky. Farther away on Mars, human beings may one day settle amid the red deserts. We can picture a morning on Mars, pale sunlight filtering through a clear dome onto gardens of green, a warm oasis in the cold landscape. In the evening, settlers might step outside in pressurized suits and see Earth as a tiny blue star rising in the dusk, a beacon of their distant home. These settlements on Mars would start out humble and fragile, small habitats sustained by ingenuity and care, tiny islands of life on a vast frontier. Each of these habitats, whether orbiting in space, on the moon, or on Mars, represents a gentle step outward. They are sanctuaries shaped by human hands in places once desolate. Within them, the familiar rhythms of daily life can flourish. Laughter, shared meals, work, rest, and even play. The dream of living among the stars becomes quietly real, unfolding one sunrise, one seedling, and one friendly conversation at a time. As we venture beyond Earth, one truth grows ever clearer. We are all travelers together, sharing the same tiny home in a vast universe. The future of humanity in space is not a tale of solitary nations planting flags, but of cooperation and unity. Already, the International Space Station has shown how people from many countries can live and work side by side in the spirit of discovery. Astronauts from different lands float together in microgravity, their varied national flags on their sleeves, yet their mission shared. In orbit, they speak a common language of science and trust. When we leave Earth, we carry with us not just individual identities, but a collective human identity. Looking ahead, international cooperation will remain the cornerstone of our expansion into space. We can imagine future moon bases and Mars outposts built and staffed by a coalition of nations. Engineers, scientists, and explorers from all over the world will contribute their expertise to these projects. Perhaps a habitat on the moon or Mars will host a crew made up of people from several continents, working in harmony under an alien sky. Around a communal table, these explorers might share a simple meal and stories of home, weaving a tapestry of Earth's cultures on a distant world. Their diversity will be their strength, each perspective adding wisdom to the new society they form. This unity will extend beyond governments. In the future, private companies, universities, and even citizen explorers from around the globe will join the adventure. All will collaborate in a shared endeavour, each bringing their innovation and passion. Just as all life on Earth forms one family, all humans beyond Earth can see themselves as members of one crew, sailing together on the same cosmic ocean. As we prepare to settle new worlds, we carry with us the lessons of Earth about living in balance. The Moon, Mars, and other destinations are not places to conquer, but places to nurture and learn from. Future explorers We'll approach these landscapes with humility, striving to make our presence sustainable for the long term. This means using local resources wisely and minimizing our footprint, so these celestial neighbors remain as unspoiled as possible. On the moon, the first travelers will likely seek out water ice hidden in shadowed craters. This precious resource can be extracted to provide drinking water and oxygen, and even fuel for rockets, giving explorers some independence from Earth. They will harness energy from sunlight, capturing it with solar panels and storing it for the long lunar night. Inside their habitats, air and water will be recycled in closed systems, each drop and each breath used and renewed thoughtfully. Greenhouses might provide food and oxygen, their plants lovingly tended as little green oases in a barren land. Through patience and ingenuity, a lunar outpost can become a self-sustaining oasis, a tiny bubble of Earth flourishing under an airless sky. On Mars, sustainability will be just as vital. Pioneers must create an Earth-like bubble from scratch, recycling everything so that nothing is wasted. Early missions will bring essential supplies, but over time, settlers will tap into Mars's own resources, drawing water from buried ice and pulling gases from the thin air to make breathable air and fuel. By using what Mars provides while respecting Mars itself, they aim to live on the red planet without spoiling it, exploring its wonders while preserving them for the future. Moving outward will happen at a mindful pace. Each new base or expedition will be planned with care for long-term effects. Before setting foot in a pristine crater or canyon, explorers will think of those who will come after and of the stories the land holds. The first footprints on alien ground will be made with reverence, knowing they might last for centuries. We will strive to tread lightly and respectfully, leaving as little trace as possible beyond knowledge gained and gratitude felt. Time in space moves at a different rhythm, marked by slow orbits and vast distances. Our expansion into the cosmos will be a gradual unfolding, like a flower opening its petals to the sun. With each decade and each generation, we venture a little farther, always thoughtful and patient. There is no rush, only an enduring curiosity guiding us outward. After establishing footholds on the Moon and Mars, our gaze will turn further into the solar system. We might build modest outposts on asteroids as stepping stones, or send explorers to the moons of the outer planets. Each step will teach us more about living in new environments. These journeys will be cautious and slow, undertaken only when we are ready, for space will quietly wait for us to explore its far corners. One day, in the distant future, our descendants might even launch voyages to other stars. Such journeys would require patience on an unprecedented scale, perhaps involving ships where generations live and pass on before reaching a new sun. Whether or not this comes to pass, the idea itself glimmers in our imagination and inspires us. It reminds us that there will always be new horizons beyond the next, and that each small step we take now is part of a journey with no end, extending life further into the gentle night of space. Each generation will play a role in this cosmic journey, carrying the torch of curiosity forward. The pioneers who first set up camp on the Moon or Mars will be followed by others, families, teachers, builders, artists, bringing the fullness of human life with them. We can imagine children growing up in these new environments, taking their first steps in low lunar gravity, or under the soft light of a Martian sky. To a child born on the moon, Earth might be a distant blue marble in the sky. To one on Mars, Earth might appear as a bright star at twilight. They will be the first to call another world home, yet they will carry in their hearts the legacy of the blue planet their ancestors came from. Life in these settlements will develop its own rhythms and traditions. Communities on the moon or Mars might celebrate new holidays, perhaps the day humans first arrived, or the moment a habitat became self-sustaining. Their art and music will be influenced by their surroundings, yet they will remain connected to our shared human heritage. Children will learn about Earth's history, languages, and arts, keeping alive the thread of memory. They will cherish the classic books and songs of Earth, even as they create new ones under alien skies. As each generation grows, they will look to the next horizon. Children who hear their grandparents' tales of traveling from Earth to Mars may dream of going further still. Under starry skies, elders will share stories of how humanity once lived only on Earth and then journeyed outward. These tales will kindle young imaginations. A child falling asleep in a lunar outpost might clutch a toy rocket, dreaming of adventures yet to come, just as a child on Earth would. And so the cycle continues. Each new generation, whether under a blue sky or a pink one, is inspired to carry humanity's quest further, fueled by the same timeless wonder. As we move outward, we carry with us the living legacy of Earth. Every spacecraft that ventures out is like a seed from our planet, containing the essence of our world's life. Our astronauts and settlers bring more than tools and machines. They bring living things, from the microbes in their bodies to the plants in their greenhouses. In doing so, they extend Earth's biosphere beyond its cradle. It is a profound and delicate task that requires us to become gentle gardeners, tending and protecting the life we bring. This awareness fosters a deep appreciation for the fragility of life. On a spaceship or a distant base, the air, water, and food that sustain everyone are precious and finite. Those who live in these habitats gain an intimate understanding of how carefully life must be supported. A single green plant in a lunar greenhouse is not just a crop, but a little piece of earth thriving where once there was only barren dust. From space, one can see how thin Earth's atmosphere is, just a delicate blue halo against the darkness. Living off Earth will deepen that perspective. When future settlers pause to look at Earth rising in the sky of the moon, or shining as a star from Mars, they will see a tiny, fragile oasis. They will know that their efforts to create a livable home on a barren world mirror the care we must take to protect the green world that gave us life. Recognizing this fragility will guide us to be guardians as well as explorers. We will strive to be protective of Earth and gentle with the new worlds we inhabit, mindful not to harm any natural wonders we encounter. Each habitat we build is like a fragile island in a vast sea of darkness, entirely reliant on careful stewardship. Acknowledging this vulnerability, we become its caretakers, ensuring that life, this rare and precious phenomenon, continues to thrive wherever we carry it. And we never forget the blue planet we come from. Our journey into space thus becomes not an escape from responsibility, but an expansion of it, guided by love and reverence. Throughout our journey, one thing remains constant: the sense of wonder that has always guided us. The night sky has inspired awe since the dawn of humanity, and that same wonder will accompany us to the moon, to Mars, and beyond. In a quiet moment on a lunar base, an explorer might step outside in a suit and stand under a sky filled with unfiltered stars. She would see countless points of light shining clear, the misty band of the Milky Way arcing overhead. In that silent grandeur, she might feel the same awe that people on Earth have felt for thousands of years, a profound connection to the cosmos and a boundless curiosity. Our place among the stars is both humble and special. We are tiny in the scale of the cosmos, yet we are also the part of the universe that can marvel at itself. We can look at Saturn's rings or a distant galaxy and recognize their beauty and significance. As we venture farther, our capacity for wonder only deepens. Each new horizon, from the cliffs of a Martian canyon to the faint glow of an exoplanet circling another sun, opens our minds to new questions and astonishments. With every discovery we make, new mysteries appear, as countless as the stars overhead. In the grand timeline of exploration, our generation is at the very beginning. We stand close to the starting line of an endless journey. Yet even now we share in something timeless. The wonder we feel when we gaze at the Milky Way is the same thread of feeling that future explorers will experience when they set foot on distant worlds. It links us to our ancestors, who once looked up without knowing what those shining dots were, and it will link us to our descendants, who may live under alien skies. Wonder is the inheritance of every explorer, past and future. It is our constant companion, guiding us gently forward among the stars. As this journey comes to a gentle close, we reflect on what it means to find our future among the stars. We have traveled in our imagination from Earth to the Moon, to Mars and beyond, guided by hope and curiosity. Along the way, we've seen that the true significance of this voyage lies not in any single destination, but in the journey itself, how it changes us, unites us, and reveals the best of our spirit. Humanity's future in space is already unfolding, step by patient step. Children yet to be born may one day live under strange new skies. This future will remain peaceful and inclusive, guided by cooperation and mutual care. People from every corner of our world will contribute to the effort, and in every new habitat, gazing back at our blue Earth will remind everyone that we all come from the same place. Through all these adventures, we will keep our eyes turned upward and outward. No matter how far we travel, we will remember the sky that first called us to explore. We will cherish the little planet that is our home, even as we step onto new ones. Standing on the threshold of new frontiers, we remain, as ever, children of the universe, curious, compassionate, and filled with wonder. In this quiet moment, think of the sky above you. The same stars shine on all of us, linking our stories across time and space. Feel the gentle pull of that infinite expanse, not as a call of ambition, but as an invitation to peace and inspiration. Our journey among the stars will continue, always unfolding beyond this moment and beyond this generation. Whenever you look up at the night sky, may you feel both humbled and uplifted, aware of how small you are, yet how connected to something vast and beautiful. Let this sense of wonder guide us as we step into the future. When a new dawn arrives, let it remind us to care for one another and for all the worlds we touch. The stars above beckon to us. In our own time, we will answer that call, together. No matter how far we journey, we will always keep looking upward and outward, with hope, with peace, and with awe.